Everybody. Thank you, Maggie. Okay, yes, I am We are recording. All right. All right. Today we're going to have more of a normal day, nominal day, shall we say? And I promised Maggie that today we would stick to the schedule rather than me making stuff up on the fly. So we actually have three different lectures today. Myself starting off with a little bit about solar wind modeling, which will take us on a little bit of a tour of models in general. And then Christina Cohen talking about SEP impacts. And then Mark Cheung will be joining us for two slots on solar data. And so that'll be our first guest lecturer for today. And so thank you for those of you who have gotten on time. I'll try and remind the others that when they come in, maybe at a break, that we should start a little bit early just to make sure everything's set up and everybody's logged in. All right, so I think we're ready to go. And I'm going to start with this presentation. Right. All right, so, oh shoot, what are you seeing? Are you seeing my slides or or the presenters?
That's the presenter's mode,
Yeah,
so swap it.
Swap.
Oh, you're good.
Excellent. All right, great. Okay, so this is actually a set of slides from Sarah McGregor, who I've worked closely with in the past. She's currently the head of the physics department at Keene State, and has worked closely with our goal here today is I want to give you some background that we're going to make use of primarily on Friday for our solar wind exercise, where we'll explore the global structure of the solar wind using the ENLA model. And in working with our guest lecturers, we discovered that this was a missing a component into what was going to be discussed, and so we decided to have me just sort of give a brief introduction to this. I'm not an expert in this, though I have a lot of experience at it, but I will do my best to give you a kind of tour as to how solar wind modeling happens and what things happen. Christina or Mark, is somebody monitoring chat?
Yep, I got it.
Okay, great, thank you. All right, so we're going to work, I want to work backwards first and then forwards. So backwards is just going to be this slide, then we'll work forwards from that. What our goal is to be able to at least predict what the plasma variables in the solar wind are going to look like at L1, right? So just upstream of us. Or maybe at Mars or at Messenger, say at Mercury. That could be another goal. At perhaps at even at New Horizons, right? So which is in the outer solar system. That there's some physics there that needs to be added that we can talk about at some other time. But we're predicting, even with all of these spacecraft all over the place, we're predicting really in situ point measurements. But in order to do that, we need to know what the global model looks like, because they all depend on each other. And so we're going to do a lot of work to get one number, well, maybe about a handful of numbers at any given time. And so The interesting thing is that the solar wind, so that relies on a solar wind model. The solar wind model, yep, we good? Great. The solar wind model relies on a solar corona model. We don't have any inputs outside of the solar corona that we can use for a regular basis. Again, we've got little buoys along the way telling us about what's happening right at that point, but we don't have a global input for that. So you have to work back to a solar corona model, and a solar corona model relies on measurements of the magnetic field at the surface of the sun. So I'm going to spend about a third of our time talking about those, about a third of the time talking about the solar corona model, and then about a third of the time talking about the solar wind model. And we'll see how far we get. All right. So, synoptic maps of magnetic fields at the sun. So this is a image of the magnetic field on the surface of the sun laid out in a Mercator. I'm not sure if this is a Mercator projection, exactly what projection this is, but this is clearly a projection where we have taken the surface of the sun, sliced it open, and laid it out flat so that we can view the whole thing at once. And so one of the important things is that we need to discuss is how is this kind of map made, right? How do we generate these kind of maps? And so Sarah has this nice quote from 1989 that you can read in Space Science Reviews, and what's disturbing about this quote is it hasn't changed much since then, right? We can compute magnetic fields, and we've gotten better and better at that with better computational methods and, of course, more powerful computers. But the difficulty is in making the measurements. Right. All right. So just a little bit of fundamentals. The measurement of the solar magnetic field relies on a quantum mechanics effect. It relies on spectroscopy. So if we look at the, you remember the Zeeman effect from your fundamental quantum mechanics. If you apply a magnetic field to an atom or a collection of atoms, the spectrum will split. You'll get splitting in some of the lines that have orbital angular momentum, and that splitting splits the energy levels, and so you get slightly different transitions in those energy levels, and so you get different energies of photons out. And so because of that, you'll see in the spectrum a splitting as shown here. So this is an example of a couple of lines that basically we're looking at a line that passes right through a sunspot. So this is an image of a blown up image of a sunspot. If we look at the spectra along this particular slit, and this amazes me that they can do this, but I haven't talked to an instrumenter about how they do this, but they look at a slit for that particular slit of light. They measure the spectrum, and then all along that slit, they can measure the splitting here, and the strength or the width of the splitting gives you the strength of the magnetic field. Right? So as the magnetic field goes up, the line gets wider and wider, and so from that, you can get the strength of the magnetic field. There is also some business about polarity. On a regular basis, I don't think that's done, but there's maybe one or two of you who are specializing in this. But this is something that people are strive to do on a regular basis now, is trying to understand the polarity and the actual direction of the. Well, sorry, no, I'm wrong about that. So there's a this gets you. This is going to get you line of sight, and what I'm thinking about is the off line of sight directions that people are working on. But it's important to know what direction, whether it's going in or out in our line of sight, so that we can get the polarity of the magnetic field. All right. So here's what happens. Once you do the Zeeman, once you use the Zeeman effect, you get you look at an image of the sun. You've got a circular disk on the sky. You look at an image of the sun. You see, you can see where the magnetic field is strong and weak, and where it's going in and where it's coming out of the surface of the sun. You assume you're only getting line of sight components, so that's challenging, and you have to make some assumptions about what that direction is. Okay. Now the other trick is what we're seeing, right? What we're observing, and so this video here, I'm going to stop it right about there. Okay, so at any given time, of course, we're only observing some portion of the sun. This is a video I got from, David Hathaway has been active in this field. You probably, if you do any solar physics, you've probably heard of him before. He's recently been joined by Lisa Upton, who is a former alum of this summer school, and is working in Boulder, and she's been working pretty intensively in solar physics as well. And they've put together a website summarizing a lot of the fundamental processes or fundamental ideas around measuring looking at the surface, observing the sun, looking at the surface of the sun, measuring its magnetic field, and try to understand the cycle. So this line here outlines what on that snapshot. So that takes a circle on a plane of sky and maps it out onto a plane, right? And so this is the circle plane of sky that we can observe. In chat, anybody notice anything a little bit odd about this observation? I gotta find the chat button. It's hidden under my camera. Oh, I can't. For some reason, I can't see the chat. If anybody's putting anything in chat.
I don't see anything so far.
Nothing so far. All right.
Nope.
Somebody's got a hand up.
There we go. Pratik has a hand up.
So I think that the portion that we can see is shifted a little bit towards the bottom, maybe because of the tilt of the axis of the sun.
Yeah, so there's something missing, and I don't know if it's of course it depends on your reference point, whether it's the tilt of the axis of the sun or the tilt of the Earth's orbit. But yeah, so there's at various points in time we're missing the poles here, right? So there's
Sam also had his hand up. I don't know if he was going to make the same comment.
Yes.
No, so I just thought that the polar regions are same. I mean, in the northern hemisphere and the southern hemisphere, the polar part is in the same direction. So maybe it is opposite of what we see. But now I can see some blue part in the northern hemisphere.
Yeah. So you're gonna. Yeah. So I see. Yeah. You certainly during, I'm not sure where we are during the solar cycle. Actually, I'll let it run for a little while. Let's see. Oh, we're just going, yeah, we're going around. Okay. And so we're going through several orbits, several, not orbits, we're going through several rotations of the sun.
Yes.
The sun is rotating every 27 days. It
Yeah.
might be a little bit hard, this is sort of the polar, color map is saturated by the magnetic active regions, which can be associated with sunspots. They aren't always associated with sunspots, but they can be associated with sunspots. And
Okay.
now so we've been through about 6 months of the year, and now we start to see more of the southern hemisphere and less of the northern hemisphere. They should be during solar minimum, the poles are typically opposite in magnetic field. During solar maximum, the bets are a little bit off, and the polar magnetic field is weaker, and the polar, that is and you get more of a toroidal magnetic field. Okay.
So Nick,
All right.
there's
Yeah.
one question in the chat or comment was the two different colors on the map and what those were related to, and then a softball question, which is going to lead into your next thing, I think, which is why are the active regions changing when they're out of the line of sight?
Okay, great. Yes, that's so I'm sorry I didn't explain the colors. The colors are actually, so yellow is, I'm not sure, I don't know if I'm going to get the polarity right, but yellow is one direction, either let's say in, and blue is the other direction out from the surface of the sun. So we're assuming, there's an assumption that the magnetic field is primarily radial at the surface of the sun, and that is a relatively good assumption, although, as I said, people are working on some other variation on that. So, and I'm glad somebody noticed that this is changing when it's not in view, right? And this is also notice what happens as it comes into view and actually gets updated. So suddenly you get some updates on what's going on as you're changing. So I'm going to talk about that, but it's going to be over the next couple of slides. Okay. Yep. Here's just another movie, sort of explaining how these synoptic maps, the individual synoptic maps, are created. So over the course of a Carrington rotation is about 27 days. Keep in mind that there's a differential rotation, so you've got it's faster at the equator and slower at the poles. So at the equator, the sun is typically rotating the material is rotating every 25 days. The poles is closer to 30 days. So the Carrington rotation kind of splits the difference, and it's 27 days. And so we've got our sun rotating here, and then over the course of 27 days, we unroll that as we observe it. We unroll that, map it out, and we get our synoptic map. And then this is something that Dave Hathaway has worked on for quite a long time. This is a nice movie showing now the evolution, Carrington rotation by Carrington rotation of these regions here over the course of several solar cycles. So here's solar minimum, where they mostly disappear, and then they appear back at solar maximum at high latitudes, and they don't migrate down, but they disappear and then reappear at lower and lower latitudes till you get back to solar minimum and then back to solar maximum. This movie only runs till the early 2000s. So that's something to keep in mind, just to emphasize that when a new solar cycle starts, we get active regions slowly starting to appear at higher latitudes, and then they appear at lower and lower latitudes throughout the solar cycle, getting more and more of them, and then by the end of the solar cycle, they only appear right around the equator. So if we can go back to here, nope. Stop, right? So now they're very close, they're relatively close to the equator, and then stop again, and now they're back at high latitudes, and there are a few other features that you should be noted about these. In particular, notice that the polarity, you've got one polar in the northern hemisphere, one polarity is leading the other polarity, and in the southern hemisphere, it's flipped. And also notice that at the beginning, at the in one solar cycle, we've got now yellow leading blue, and if I skip ahead a solar cycle, still yellow leading blue. Now blue's leading yellow. Right. So, few things about that. All right. This just gives you some of the details about how these synoptic maps are put together, showing that at any given time, you take the image of the sun, you spread it out you do the transformation onto a flat plane, you take the middle of that and average it in using a weighting function to what you already have had. And then what you're going to do is, so that you've got a full Carrington rotation here, but now what you're going to do is shift that over a day and play the same game over and over until you have a full Carrington map for the entire rotation. All right. I just want to give you a question. So here's some assumptions about the synoptic maps. One of the things that we assume is that it's stable over 27 days, right? That more or less these, okay. As I already said, the photosphere, when I say the solar surface, what I really mean is the photosphere, where the sun becomes opaque, the magnetic field is radial, and there's good evidence that this is true, except in very strong active regions. So I want you to think about this for a minute. Which of these problems do you think is we need to correct for? And so you can indicate this by just using the annotate tool and putting a star or a check or something by the one you think is the most problematic for our observations of the sun.
Pauline wants to know what you mean by static. Number 3, I assume.
Oh, so so as an active region, a magnetic field rotates off the back to the backside of the sun, that my last observation is still good. We've got a heart for 2 and 3. Any others? One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's about a third of you. 4. Okay. All right. last chance to get in on this. 6, 10, 11, 12, 13, 14. Okay, great. So we've talked about a couple of these already, and in truth, all of them are problematic. So let's talk about what has to be done. So there's a number of corrections that have to be done. So the big one, well, I don't know if it's the big one, but one of the ones that's important is like del dot B has to be 0. Right. So the total net flux over the entire map has to stay has to go away, right? We also need to do something about the polar fields, and so if you've got no observation there, you need to do something, and then we need to use some kind of flux transport process, which people are working on today, to figure out how to evolve the active regions as they go out of view. All right. So one example. So here's a problematic map. So this is an uncorrected map that has been taken. It's been observed. What do you notice about the green areas there? I can't see anybody, so I want you to think about what you notice about this green area here. So this is where the new data has been taken on the left-hand side here. It's a little counterintuitive, but we're thinking about how the sun rotates, and the sun rotates from left to right in our view. So we're adding, as new features come over the horizon, we're adding those onto the left-hand side of the map. And so these are the new features over here. Notice that this guy has a lot of one type of polarity, the white polarity, and there's none of the black polarity to balance it out. Maybe there's a little bit here, but given the sequence of white, black, white, black, white, black, you expect that there should be a white spot, a black spot on the left-hand side. Keep in mind that each of these combinations are usually single sunspots, right? So, so there should be a black polarity that's combined with the white polarity. And notice that when we've taken a few more observations and we've extended this a couple of days, that this region here and this region here are the same region. And so now you've got the black polarity. So what happened was an active region emerged on the backside of the sun while we couldn't see it. And we only see the leading polarity as it rotates around to the front side. And so that means that we have to somehow do a correction for that. So we have to make some assumptions about what's happening to the net magnetic field. And there's various ways of doing this. I'm not going to go into all the details about how that happens.
Nick, Stephen wants to know, doesn't this prove the 27-day stability is a bad assumption?
Yes. Yeah. So, but it's the only thing we can do. So we can't, right now it's the only thing we can do. So what you have to acknowledge that it is not as good an assumption as it could be, and make corrections for it and account for it somehow. Does that help?
Hopefully. He hasn't responded, but we'll see. If not, I'll interrupt you again. Or Stephen can just speak himself.
Thank you.
Okay, great. And I'll come back to that. I'll also come back to that in a minute. I want to get through a a couple of more things. One of the things to notice, if I go, can I go back? I'm trying to go back. There we go. One of the things to notice is the roughness of these things at the poles. Keep in mind, when you spread something out like this, the polar regions become much larger. They appear much larger than they actually are. So you're taking a lot of field here and spreading it out over a smaller area. So you're really smearing things out. Appears than it actually is. But the other thing is, as people already pointed out, the inclination of the Earth's orbit to the sun's rotational axis or the sun's rotational equator, I should say, it's about 7 degrees. So during some parts of the year, we can't see the southern pole. During other parts of the year, we can't see the northern pole. And so some assumptions have to be made about how that's supposed to work. And so you have to do some filling or some averaging over that in order to get a complete map. The interesting thing is that, and so what you end up getting is that you can get a very noisy pole because of the averaging, because you're spreading it out through over a very large area, but also because the averaging, because you have to make some assumptions about what it's going to look like at the poles. All right. And so you can get a noisy boundary. Part of the noisy boundary is the fact that we don't have a lot of, because we're also looking at the rim of the sun. We're not getting true line of sight measurements. We're getting like some very small component of that measurement. So we're getting a lot of noise in the measurement of the magnetic field strength and polarity. And then we've got to fill in the missing data. So you've got to make some guesses about what the strength is based on either what you observe in the North Pole or some other guesses about some other observations about it. Again, assuming that the total magnetic field, the total flux is going to be 0.
Nick,
Yep.
Raphael wants to know what other kind of assumptions you're making are made or can be made to correct the poles measurements.
I don't know. So if you have any good answers to that question, I mean, I know that you do some averaging and you do some and the total flux has got to be 0. So I don't know if you have any good answers to that question.
Oh, Mark Cheung, are you going to talk about this during your talk at the end of the week? He says the next slide sort of answer that question. So there you go.
Oh, adapt.
Yes, because you evolve the whole map and it includes the transport of the flux by the meridional flow and the supergranular diffusion towards the poles. So that's one way to fill in the gap.
Yes. So this has been ongoing for a while, but this is, and I think this slide is a little old, but this is the state of the art right now, is to use what we know about differential rotation and meridional flows and diffusion to start to, and this also helps. So to start to fill in the gaps, this also helps as we're moving around as we're looking at the back side and trying to update the magnetic fields on the back side. So I didn't realize we had an expert in the room already. So The other interesting thing about this is
So
that
also, Nick, related to this, Miguel asked about the magnetic fields being calculated at the limbs,
yeah,
right? And so, I was just about to type that technically we can measure those, but those measurements are not very good because it's a line of sight and you're looking not perpendicular to the surface of the sun. So we often don't
Yeah.
use those. We use this to kind of fill in those edges as well.
yeah, yeah. Thank you for explaining that. I did not explain that very well.
Yeah.
I believe the other thing that they're using with ADAPT, and that is a current add-on, is the helioseismology. So that gets us information about the backside through the Doppler shift of the surface of the sun on the front side, and so we can see that and back out what's happening from the backside and see what's going on there. So I think all of that information, trying to use it all to try and get that information is what is the future of ADAPT, and that is, it's not operational. My understanding, the last talk I saw was in June, is it's not operational, but it is something that they're continuing to develop. All right, I am going to skip ahead. We've got the inputs to this. Shoot, I wanted to see what time it was. Okay. I've got about 15 minutes left. All right. I spent a lot of time on that input, and it's important to understand that is the strengths and weaknesses of that input, because it's the thing that drives everything else. Once you've got that input, there's a couple of different possible approaches. One is the MHD around a sphere, and so it's a full physics model using MHD first principles models to build out the whole corona and understand what the plasma is doing throughout the whole corona. The other approach is the Wang-Shiui-Argy approach, and that's the one I'm going to briefly go over. We spent a little bit of time with Carl on that on Monday, and it's a potential source surface model. And this is a semi-empirical model that just gets you the magnetic field structure, and then you have to make some assumptions about what the plasma is doing, and I'll go over what those assumptions are. So the Wang-Shiui-Argy model, Nick Argy is still actively developing this, and he's also his biggest input is working on ADAPT and trying to make the magnetic field inputs better for this. This is going to get you a steady state solution. That is, you're going to, for a given synoptic map, you're going to get the magnetic field for that map, which, as we already said, unless you're updating, unless somehow you've got some dynamics for that map, that steady state solution has some issues with it. It gets you the magnetic field. It makes some assumptions about the magnetic field, that it is all the closed field lines, only. Whoops, I'm pointing to an image you can't see. I'm going to go to the next image. Okay, so you'll remember Carl's exercise with the charges and the mirror surface, right, and the mirror image. You're doing the same thing here, but now you're doing in the spherical geometry. The charges represent the magnetic field on the surface of the sun. The mirror image, or the mirrors, the surface is this point here, where they assume all the field lines are closed, and then beyond that point, the field lines are all quote unquote open, which basically means that they continue out to the end of the outer boundary. And so then we can use that and solve the potential equation, and then from that back out the magnetic field. All right. So we get a full magnetic field structure. I'm gonna zoom ahead just a little bit because more about modeling the magnetic field. But once you get a full magnetic field structure, you can then map out what the magnetic field looks like on the outer boundary. And this outer boundary is only about 20 solar radii for, if you were doing for the MHD models, they sometimes go out to about 30 solar radii. Pick your order 10 solar radii boundary that you think is appropriate. So that's how far out it gets you modeling the magnetic field in the solar corona. And so then you can take you can take the outer boundary and then map that onto a map here that shows the different, in this case, just the polarities of the magnetic field. You can also get the strengths of the magnetic field here too. If I do this, and I'll take some examples in chat. I solve this potential source surface model, and I get the magnetic field. I now want to feed this into a solar wind model. What else do I need? If I want to run if I want to feed this into the inner boundary of a solar wind model, what else is needed? So you put either speak up or put your answers in chat.
Okay, Pratik, it's got velocity, density, and pressure.
Okay, great. That probably covers most of it. Yes. So this is a time out to think question that I had in here. One of the things that I wanted to get out of this is what you're not going to get is out of these potential source surface models is you're certainly not going to get any idea of what the temperature of the plasma is in that corona and the density and the velocity. So you because white light coronas the coronagraphs tend to model the magnetic field. You can make some predictions about what the white light coronagraph will look like, but it's going to be difficult to get any idea of what the extreme UV images are going to look like because you don't have any temperature, you don't have any pressure, you don't have any density. And so, again, skipping ahead because I want to make sure that we get onto this. So on the outer surface, you can get what the magnetic field looks like. Again, this is just showing the polarity. And then that's starting from the photospheric field. We don't get a velocity from this model. So really quickly, what you can use is an empirical relationship that has been derived for or measured for the solar wind velocities that shows that when you get that relies on this thing called the expansion factor, right? So here you've got a solar magnetic field, say near the poles. it's still pretty dense. It's moving out on order 1 over r squared. It gets wider and wider. So you can imagine that if this is a flux tube, as the flux tube opens up, the solar wind starts to slow down some, but it doesn't. If it doesn't open up very wide, it continues out at a pretty good clip. On the other hand, you see this flux tube here that's coming down, covering a helmet streamer, right? So this is where you would start to see trapped plasma in your helmet streamers at solar minimum. And as that flux tube opens up, that solar wind's going to slow down even more. So you can use this expansion factor and the ratio of the magnetic field on the surface to the magnetic field at the source surface here at that 2.5 solar radii, and see what that expansion factor is, and from that get a relationship for the velocity. You also then have to make some assumptions about the density. And then with that, so this is just the what happens, how you estimate the speed using the expansion factor and the foot point boundary terms. This slide is a lot cuter when Sarah does it. I'm not good at cheering, so but she has this little chant that she does about how we make a magnetic field that we then feed into the solar wind.
Hey, Nick.
Yep.
Asna wants to know if the expansion depends on the direction of the magnetic field or anything else.
It won't depend on I don't think it depends directly on the magnetic field. There's certainly what you don't get out of the potential source surface is it's sort of magnetic field direction agnostic, right? Is my understanding. I've got about 2 minutes left. And what I promised to do was get to the solar wind. So here's a solar wind presentation in 2 minutes. I'll come back to some of this when we do the solar wind lab. The solar wind models are, there are some empirical solar wind models, and you can do a wide variety of things with the solar wind. The ones that we're going to be looking at are going to be MHD models, so they're going to be physics-based models, where you use a combination of Maxwell's equations, Ohm's law, and mass and momentum continuity, right? All the MHD equations, and you need a pressure term or a pressure relationship between pressure and an equation of state relationship between pressure and density. The inner bound. The important thing is that the inner boundary of this is where the solar corona fits, and it says this one says it's 30 solar radii. If we're using Wang-Shui RG, of course we have to pick it up at 21 solar radii. And what happens is you take in this space here, you've got your solar corona model in this empty region. And it fits right in there. And what you're going to do is it's a static model. So over 27 days, we're saying that doesn't change. In the future, we may be able to make it a dynamic model. But for now, they're taking a static model. You put the solar corona model in here. Take your assumptions about your plasma parameters, the magnetic field that comes directly from the model, the velocity that you get from the expansion factor, assumptions that you have about the density, which I haven't gone over, and pressure, and temperature. and you paste those on the inner boundary of your MHD model. And then you take a time step and you evolve the MHD model so that solar wind starts to move out from this inner boundary. Then you rotate your solar corona model by whatever your time step is. So whatever that time step is, the angle that the sun rotates in through its Carrington rotation, and now you paste the new variables onto the inner boundary. And solar corona that you start to feed out. Is this a movie? It is not a movie. No, it's a link. Oh, phooey. I'll have to find this link is dead, so I'll have to find it. But slowly over time, so this is now a equatorial cut through a 3D model where again, this is this inner boundary. This sun is way too big, so this is the 21 solar radii inner boundary, and you're pasting the values of the solar corona model onto that inner boundary, evolving those out, and because you're rotating the inner boundary, you're rotating what you're pasting onto the inner boundary, you're going to get the so-called Carrington or Parker spiral rotation as that inner boundary rotates around, and you get, say, for example, whatever this coronal hole is blasting out high-speed solar wind, that's going to move around. The wind itself is going to move out radially, and this is something that we want to work on when we get to the solar wind model. But you get this structure that looks like the Parker spiral, and of course you're wrapping up the magnetic field at the same time because you're constantly changing the position where that magnetic field foot point is as you rotate the inner boundary. All right, that was a really fast tour of this, and we will return to a little bit of this when we look at the solar wind models in the lab on Friday, and I'm sure our solar wind modeler will talk about that. I'm trying to remember our lecturer's name for the solar wind model, and I can't.
Joe Giacalone is going to talk about the solar wind modeling.
Oh, that's right. Yes. Okay.
So Nick, I know you're over time and you promised Maggie you'd stay in time, but there's a couple of questions in the chat. I don't know whether you want to just answer those in the chat during the break, or how you want to, or whether you want to take them now.
I'll look in the chat. How close, sun, can we use MHD? So I can tell. Well, you can talk more about those, but MHD. So there's in the solar wind. I think the biggest difference is the equation of state. So the solar wind assumes one type of equation of state. You can use MHD. So the mass model, MHD around a sphere, actually uses MHD to solve the solar corona model rather than using the empirical model that I described. We may get more information about that as the week progresses. So you can use MHD, and so John Linker's group, as an example, uses MHD around the sphere, and they've become experts at predicting solar corona using MHD. And then expansion, is the expansion dependent? Oh, okay. So it assumes that the inner boundary co-rotates with the sun. Yes. So that is so they're assuming that the whole solar corona is essentially co-rotating with the sun.
And this does also include the differential rotation at different latitudes, or how far do they go there?
So that would be a way, if we wanted to update the synoptic map on a regular basis, we would want to include that as a, so that's part of what ADAPT is trying to do.
Thanks.
Okay, great. I'll be, so we will have our, during our longer break, sorry, that's my air conditioner making a lot of noise. I'm yelling over it. During our longer break, after Christina's talk, we will, I'll be around and we can talk about any of the details and I'll answer the questions as best I can. Okay? All right. So Christina, can we come back at 11:05?
Sure.
Okay, great. And we'll start with we'll go with your talk. Okay, got a thumbs up from Mark. That's good. All right. I think we're getting most. Looks like most everybody is back on. So why don't we move on to Christina Cohen talking about SEPs and their impacts.
Yep. Okay, so let's see. Let me find my PowerPoint. Okay, and I'm going to rely on Nick or somebody to let me know if anybody's got a hand raised or question in the chat. Feel free to interrupt. I'm going to also say that the other thing you can do if you're feeling the annotation thing, you can also just maybe put a stamp like a question mark on one of my slides and I'll stop and you can actually unmute and ask a question. So, okay, so we're going to go through SEPs, space weather impacts and why we care. This is one of my favorite slides actually, because all the little pieces that you're seeing here, it's sometimes hard. Let me just get a pointer going. It's sometimes hard to like visualize SEPs, so to speak, but this is one way we can actually see them. What you're seeing, all these speckles, is actually SEPs hitting the detector from the LASCO instrument on the SOHO spacecraft. Okay, so space weather. So this is a cute animation, and obviously it's not exactly realistic, but you know, many of you have heard about space weather. It relates to flares, it relates to coronal mass ejections, and of course solar energetic particles, which is mostly what I'm going to focus on, and also geomagnetic storms, which was the exercise from yesterday, where you have a CME that impinges on the Earth's magnetic field. It causes reconnection. That translates to disturbances down the tail. And then one of the things that can happen is this reconnection in the tail that drives the pretty aurora that we see. But you can also have SEPs that come directly down and hit the atmosphere and all kinds of other things. So we're going to talk about some of that stuff. Okay, so space weather, why is it bad? Well, it causes a lot of problems. For one thing, the radiation, so the actual particles that hit you, they are bad for all kinds of things, including spacecraft, and we'll talk about each of these a little bit in the following. It's bad for astronauts, just like any other radiation exposure. If you have too much of it, it causes changes in your body and can cause all kinds of things, including death, which is not a good thing. And airlines, it's when we have a lot of airlines that are going over the poles, through that sort of open magnetic field in the Earth's magnetic field structure, you can get radiation coming straight down. So that can be a problem. We talked about this some before, ionosphere. You'll hear more about that later, probably next week. But you know, the X-rays and also the particles can change the ionospheric composition. The chart, you can charge it. And that can affect our radio communication. The radio waves don't propagate off of the ionosphere the way we expect them to, and that causes problems for communications, as well as we have problems with GPS positioning, as we also talked about the other day. And then there are geomagnetic effects, and this has to do with the change in the Earth's magnetic field being either squished or reconfigured, and that can do a whole bunch of things. It can cause problems for the power grid. You can actually have effects in the pipelines carrying oil, and of course it affects communication as well. So here's just a quick sort of overview on how that works. Is basically you can get these large currents that are induced due to these changes in the magnetic field, and how those currents propagate or change kind of depends on the makeup of the earth at any given point. So if you have more minerals or more rocks or more salt water, you can get different kinds of currents. And of course, if you have a voltage gradient or a current going through, that's going to induce a magnetic field above it and around it, and then that can induce a current and a change in voltage in, say, the power lines. And so that can cause a big problem. So the power grid people are actually big concerned about these geomagnetic effects, and with good reason. So there's been big examples. This is the example everybody likes to use, that there was a big geomagnetic storm in March of 1989, and this whole section of Quebec that was run by Hydro-Quebec was the power grid, basically went blank. You know, they lost power. These are the big transformers that take the current and the power and the voltage that's going through those lines, and they convert them into what you need in the wall socket of your house. And you know, the right voltages and currents to run all the things that we want. And they're built to handle certain amounts of voltage and current. And when that changed, they basically melted. And you can see these things are huge, and they are not something that and they're very expensive, and they take a while to build. And so they're not something that we just have a whole bunch of them sort of lying around and we can just sort of swap them out. So when you have some transformer damage kind of thing, it can be a very big problem. And in fact, this is sort of a map of where this effect was in the United States. And this whole section here was run by Hydro-Quebec, and they basically lost power for 9 hours in March when it's cold. And there were lots of problems. Lots of people didn't have any heat. It was a pretty distressing thing. They also had damage of equipment, which is these little pink dots here. But you can see that this is an old figure actually in terms of where the different grids are sort of connected. And in fact, we have more interconnectability or interconnectedness now than we used to. And so even with this, you would see that there were places where equipment tripped all over these different areas. There was other damage to other equipment. And you can see how this, you know, can quickly become a sort of a more, and this is just the United States, there's actually bigger regions, then it can become a global effect. So this is just going to be a fun little exercise. I know you guys are used to the annotate, so I'm going to just ask you to sort of vote with your stamps as to how much you think per day. Now we're talking about not overall of the cost of the storm, but cost per day due to a blackout in a solar storm. And I'm just looking at rough categories here, whether you think it's thousands of dollars, and I apologize that I'm using dollars, not like euros or something else, but we'll just start with dollars because that's the report I have. Thousands of dollars, hundreds of thousands of dollars, millions of dollars, hundreds of millions, or billions of dollars, or more than billions of dollars. And remember, this is per day. So we're talking about, you know, potentially a lot of money if it extends for many days. And so I'm just going to wait a little bit. And I see people are putting stamps in there. That's great. Seems like a lot of people think hundreds of millions. Few people think billions. Okay, looks like it's slowing down. All right. And if anybody, I know some people can't put a stamp in because they're on the web page. So maybe if they put it in the chat, maybe Mark, you or Nick can put a stamp on there for them if they have a vote. So. All right. Nick put an arrow at millions of dollars. Okay, we will move on. So this is actually a, you know, pretty good guess. I think I would have thought, you know, since we're talking about per day, I'm thinking millions of dollars. That's a lot of money, even hundreds of million dollars. That seems insane. Well, this is the report that came out. Oops, now it doesn't seem to want to advance my slides. Interesting. Okay, let's see. I'll do it this way. And I'm not sure I can get rid of all the annotations.
I got it.
But anyway, so I may have little dots all over the rest of my slides. So I wonder if I can annotate and clear everything. Oh, I actually don't. Clear.
So Meg,
Oops.
can you use under the annotate?
There we
You
go.
should be able to.
I got it. Yep.
Great, thank you.
The problem is with my laser pointer, it now doesn't show me my mouse, so it's all very confusing. But anyway, and now I think I've lost my laser pointer, which seems to have decided not to play nice. Okay, so this is interesting. I can't get rid of, there we go. Okay, sorry. All right, so this was actually a report that was done, I don't know, I should have had the date here, but I think it was done about 10 years ago. So this is kind of dated, and basically the cost that was estimated from a blackout is $40 billion a day. So that's like the highest level that I had in there. So some of you are correct. I was actually astounded when I heard about this. And part of this is, you know, about half of this or so has to do with direct effects, meaning, you know, your store lost power and so you can't sell anything anymore. And so you're going to lose money every day that goes by, that you don't have power, that you can't, you know, store things. And obviously, as it goes along longer and longer, if you have a grocery store and you don't have any power, you start to lose all your frozen food and all kinds of things, stuff that people who have, if anybody in your house, if you've lost power for more than a few days, you know that eventually you lose everything in your refrigerator because your refrigerator is not keeping things cold. So, and I also, but indirect effects are actually pretty big. And I was thinking about this in terms of, we've had real clear experiences of this with the pandemic, right? So I'm here in the US and I want to buy a new car or something like that. And while the cars can all be built here and there's nothing, no problem maybe with the workers here in the US, but if somebody, if like Taiwan is all shut down and not building semiconductors or chips that we need for the car, then the cars can't be built because of something that's happening in Taiwan. So you have this supply chain, which is now so global that if something bad happens in one area of the world, it can affect everywhere else. And so we've seen that with COVID. That's the same sort of thing that you can get from these solar storms, is if you shut down an area for an extended period of time because of a blackout, then it doesn't affect just that area. It actually costs money for everybody all around. Okay, so so basically the US government, among other governments, have recognized that this is actually a big threat. There's a bunch of problems. You can have, including SEP events, which what we were just talking about was not so much SEP events, but the geomagnetic storm. And they've put together this group and this National Space Weather Strategy Action Plan, which they call SWAP. And they even passed a bill that says, hey, we really need to pay attention to this. Some of this stuff comes with a little money. Some of it sort of says, hey, we think it's really important and somebody should fund this. And so, you know, at least they're now paying attention that it's not just astronauts, but it's spacecraft, communications, all kinds of things that we need to pay attention to. Okay, so let's talk about specifically SEPs and their impact. In terms of spacecraft. So here's sort of a whole list of things that can go wrong. This little example here was actually the slide I showed at the beginning, where this is a LASCO image. When the SEPs come, they degrade this image by impacting the detector and actually causing spurious signals. But you can also get signals in any kind of instrument, which the instrument can actually interpret incorrectly. Sometimes it's just noisy, it makes your data noisy, but sometimes it causes false alarms. It can actually do what we call single event upsets, which basically in the electronics will flip a bit from a 1 to a 0 or a 0 to a 1, and suddenly the instrument thinks it's gotten a command or something that it needs to do. And that can cause all kinds of problems. It can change gains in your detectors, which allows you, affects your measurements. It can cause problems for sensors in terms of the attitude control of the spacecraft. You can also have just the whole spacecraft or the instruments can go into a safe hold where they go, I don't know what just happened, and I'm just going to shut down and try and keep myself safe for a little while until I hear what to do next. So that, of course, means you've lost data or lost mission information. Latch ups, you can go into sort of this sort of confused mode where it just sort of freezes and doesn't know what to do. If the SCPs hit the solar rays, a lot of our spacecraft have solar rays, and that's how they get their power. You can actually have discharge. You can actually cause problems with the different cells. And so that all affects the total amount of power you have. And so it can degrade that over time. You can actually just do something that just totally messes up the whole instrument, or even the spacecraft. You can actually lose the entire mission. And so I'm going to show you a few examples, real life examples of these things. This was a plot of the number of spacecraft, and this kind of relates to what we were talking about, the Starlink example yesterday, where a spacecraft, for whatever reason, has re-entered the atmosphere. Now, this could come, in a lot of cases, this is because the ionosphere, just what we talked about with Starlink, has puffed up. And so now there's more drag on the spacecraft. And if the spacecraft isn't able to sort of adjust its height or shift, it could actually be dragged down and re-enter the Earth's atmosphere. And of course, then it disintegrates and does all kinds of bad things. But it can also be that the spacecraft, suddenly loses its ability to maintain its altitude and things like that. So they just found, they didn't really try and classify what caused it, but they plotted the number of spacecraft that re-entered and as a function of time. And then they also plotted the sunspot number, which is this pink here, which is sort of a proxy for activity on the sun and therefore space weather. And you can see that they're pretty well correlated. So, these things are happening much more frequently when you have a lot of space weather. So here's some other fun examples, and I apologize, these are probably all examples that seem recent to me, but are probably all when you guys were little kids. But there are more recent ones, but this is a very famous storm that a lot of people talk about. It was a series of events that happened in October and November of 2003. You can see these are some of the data that we have. Again, you can see the degradation from the SCPs. There was this active region, it went off, it created a very fast CME and a very large flare. And basically Mars Odyssey orbiter spacecraft was going out and it entered into a safe mode. And the spacecraft actually had a memory error that they actually took them several days to have to do a cold reboot in October. And the marine instrument that was there had a temperature red alarm, which caused them to power off, and they actually never came back up. So this is an example where we actually lost a particular instrument. The twin Mars rover spacecraft that was en route to Mars both went into a sun idle mode. Luckily, those recovered, and so we were able to bring the rover to Mars. Astronauts in the International Space Station actually had to go into a particular module for their radiation protection. And I'll talk about, again, a little more effects on astronauts later. The FAA issued its first ever alert about radiation doses for passengers that are on airlines that are going above 25,000 feet, particularly over the poles, because the radiation they were going to expose to, because the spacecraft doesn't provide all that much protection, was going to be enhanced. And so they actually put out an alert, and I don't know if they actually diverted the airlines on that case, but that is something that they found was a concern. And of course, in Sweden, they actually had a power system failure for a day. Okay, so December 2006, there was a huge flare that went off on the sun, and it was recorded as 10 times more intense in this particular area than ever on record for the entire sun. And in case here, in terms of radio, it was 20,000 times more radio emission than the entire side of the sun. So basically, everything that was facing the sun on Earth, the GPS receivers, all got completely swamped. And so none of them could do their signals and their jobs during this time period. Luckily, this was fairly short-lived in terms of the radio, but it did have a big effect on all the GPS receivers. This is one of my favorite ones. April 2010, there was actually a Intelsat's Galaxy 15 satellite had suddenly stopped responding. Basically, there was we don't know exactly what happened to it, but it was it stopped receiving and communicating with Earth, so we couldn't actually point it or stop where it was, and it was drifting. It was actually broadcasting signals in just sort of random directions, and it was drifting across all these other areas that other satellites were. And so there was this big, it was called the zombie sat for a long time, because we just couldn't actually get it to do, to stop and respond to our commands. And there was some concern that it was going to interfere with a bunch of other spacecraft, including TV spacecraft that were at the time broadcasting the final episodes of Lost, which was a big TV series that lots of people were fascinated by at the time. And there was some worry that this zombie sat was going to go through this broadcast and interrupt it during the time that we're going to have the final reveal. This was actually recovered. They managed to actually finally get the spacecraft under control, and everybody found out what Lost happened, what the ending of Lost was. So, whoops, too fast. Okay, let's talk about humans.
Christina.
So, yeah. Nick.
Oh, yes. Okay, great. So, yeah, we've got a few questions, and that's been handled already.
Okay.
In terms of,
I can't see the chat.
One of the questions, yep, one of your slides had a radiation symbol on it.
Yep.
With the one that was talking about
this one.
Yeah, I'm lagging. So that one, yes, right. So I don't know what the what was the intent of the radiation symbol.
So the radiation symbol was that you could actually, if you irradiate material long enough, it itself can become radioactive. So if you have a section of your spacecraft which is now radioactive, that can cause problems for all kinds of things, as you can imagine. So that's what that little symbol means right there.
And there was also a question about whether certain spacecraft were hardened or protected against SEPs. We got a couple of people commenting that there's some shielding that are put in to protect them. I don't know if you've got anything else to say about that.
Yeah, so there's a bunch of things you can do. So we do make electronic components, which are called radiation hard, but they're only radiation hard up to a certain level, right? So at some level, if you bombard it with enough energetic particles of certain energies or even certain masses, or enough of them, they'll fail or they'll have problems. And so we can design these things to be protected against some of these effects. But as with everything, the protections you put in cost money, right? And so the same thing with shielding. So you can put shields around things, and we do, but that adds weight and all these things. So mass, power, and space basically is the things that you are concerned about a spacecraft, right? Is you only have so much capacity to put a spacecraft of a certain weight up into space. And so if you put really heavy instruments on there, then you can't put as many instruments on there. And if the instruments need a lot of power, then you can't put as many instruments on there, and so forth. So you have limited resources when you put something up. And also, if you want to put up a huge spacecraft, then that's going to cost a lot more money maybe than one or two smaller spacecraft. So there are all these trade-offs in terms of cost versus design versus capabilities. And so you don't want to over design something. So you don't want to shield it more than you need to. And the question is, how much do you need to shield it? And of course, certain things like this, you can't really shield the front opening of your detector if that's what you're trying to, you need that open to receive your say photons or even your particles. The irony is there have been situations where an energetic particle detector that's supposed to be measuring energetic particles has been killed by energetic particles. So there have been cases where even what you're trying to detect can kill you. So there are things we can do, but we can't completely shield everything. And that'll actually be relevant to this, which is astronauts. The spacesuit itself doesn't provide lots of protection. It provides some. So if the astronauts are out on a spacewalk and a SEP event comes by, they're probably going to have a lot of problems, depending on how big that radiation level is, right? So they can get cataracts, they can increase their chances of getting cancer in general. They can actually have problems to neurological problems, effects to their stem cells, all kinds. It can just radiation sickness can just make them sick, all kinds of things. Now, if they have warning or they're already in this, so then of course, say like the ISS or once upon a time when we had the space shuttle, if they were in there, that provides more shielding. And so that's more protection, but again, it's still not everything. And then but we have built areas or trained astronauts to kind of make a shelter out of stuff that's in the spacecraft. So like if they're going up on, sort of on SpaceX or something, then they have been trained to like take things and make a shelter and get inside that shelter. But you can only do that if you have enough warning, right? So you have to have enough time to either come back from your spacewalk or to build your shelter or go to another place in, say, the ISS, which is more shielded, and you have to wait there until basically the event is over. So that's one of the things that we want to protect the astronauts, but we need to know and be able to predict these things, which is going to be the whole second half of my talk, which hopefully I'll get to. So this was what I mentioned before, is that we have a lot of flights now that are going over the poles of Earth. And that's where you have more of these open magnetic fields. And so the SEPs can come straight down and they can cause problems. The airlines can reroute these flights if they need to, again, if they have warning, but it's really expensive for them to do that. As you all know, delays in airlines, changing, routes and stuff like that can cause all kinds of chaos, not just for that flight, but all the subsequent flights. So they don't like to do that if they really don't have to. Okay, and then of course, SEP's events are not a hazard just near Earth. We've been focusing on that, but we have satellites now all over the place, including at Mars, and maybe someday we might even have people there. We certainly have rovers there, and so space weather is an issue for lots of other locations other than just Earth, and it happens everywhere. Okay, so I just threw this in, is that there's lots of other reasons to study SEPs, not just for space weather reasons. The sun is very cool. SEPs tell us a lot about the activity and stuff that's going on in the sun, including its composition. It's also our closest star. So if we understand the sun, that helps us understand potentially other systems, in particular exoplanets and their effects from their local sun. Acceleration, which drives these particles, this happens everywhere. I think this was mentioned in Carl's talk. I'll talk a little bit about the CME driving the shock that's accelerating particles. We also have shocks at ahead of the Earth, the bow shock. You see them in stellar systems. You see them in our whole heliosphere. We have the termination shock, which is ahead of our heliosphere as it moves through the interstellar medium. And all of these guys accelerate particles. So understanding what's happening close to the sun in terms of these helps us understand all this stuff. There's also reconnection, which can also accelerate particles, which I'm not going to talk quite as much about, but that also happens everywhere. This is just different images on the sun showing this reconnection here, a really neat event. But it also happens, as that first movie showed, at the front of the Earth's magnetosphere, you get this reconnection, but also in the tail, which leads to the aurora and all kinds of other aspects in the Earth's actual magnetosphere. Sorry, this is Jupiter. So you get the same effect in Jupiter that can cause the Jovian aurora as well. So understanding this reconnection and accelerating in particles helps us understand all these other systems. Okay, so let's talk about what specifically SEPs are. So this is pretty easy. They're solar energetic particles. Solar meaning they come from the sun. Energetic This is a little bit in the eye of the beholder, but it's historically they're above a few hundred keV per nucleon. So, and that becomes of interest because it used to be we just looked at protons, but now we're looking at all kinds of ions, heavy ions all the way up through iron, and we've seen zinc and things higher than that. Particles, they are ions and electrons, so they're usually not quite fully stripped. The lighter ones like protons, of course, are fully stripped. Helium is usually fully stripped, so it's helium plus 2. You have carbon, nitrogen, oxygen, all the way up, as I mentioned, to helium. So we are measuring all of these. And this is an example of where this falls in the sort of the grand scheme of things. So you're looking at particles. This happens to be oxygen, integrated over many years. As a function of energy. In this case, the units is MeV per nucleon. And so what you see at the low energies is the peak around the solar wind. So you have a lot of particles that are coming out that are part of the solar wind, and you'll hear about this later, I think tomorrow, and the fast solar wind. And then you end up with this sort of tail on the solar wind. And then all this stuff is basically energetic particles. And they can come from a bunch of different types of energetic particles, which I'll talk about later. And if you get up to high enough energies, you're talking about galactic cosmic rays, which are coming from outside our heliosphere. And I'm not going to talk about those at all. And so we often have instrumentation. This is for one particular spacecraft that is trying to, we can't really measure this entire distribution with one instrument for a bunch of different reasons, because there's different methodologies on how to measure these, but we can kind of cobble together a bunch of instruments to try and cover this whole range. Okay, so how they're measured. Most of the stuff that's measured right now is space-based instrumentation. So what you've heard about, like ACE and GOES, there's a bunch of other spacecraft that I'll mention along the ways. We also can measure them on the ground indirectly through neutron monitors. And basically, a particle will come into the Earth's atmosphere and it will interact with the atmosphere and it will create what's called the shower. And it will create all these different secondary particles, which can then actually be measured on the ground. And if you understand and can model this backwards, then you can kind of take what you measured on the ground and back it out. Now, you can only measure this stuff if you have enough of these particles that are energetic enough to make it down to the atmosphere where they actually interact. So that's another aspect, a limitation of that measurements, but we'll talk about that a little bit later. So this is one type of common methodology for measuring SEPs. It's called the time of flight. So basically a particle comes in here and there's sort of two pairs here, but basically, excuse me, it goes through a foil, which kicks off an electron, which due to these little grids will be deflected towards this detector on the side, which will give you an electrical signal, which we call the start signal. The ion itself goes through this grid and keeps going, and it passes through, say, another foil, which can kick off another electron, which can give you sort of another time period of when it passed this. And then it can also, in some cases, we don't have this center one, it can eventually hit the back of the of the instrument, where it can be measured its total energy. It also kicks off an electron, which will then be measured here. And so you now have measurements of how long it took this particle to go from this distance to this distance to this distance, and a total energy. And from that, from simple calculations, you have a velocity because you know this distance and you know its total energy, and you can calculate its mass and all kinds of interesting things from there. That doesn't work as well because those things are usually small. And so if you have a really fast particle, you don't have the electronics that are fast enough to measure that, you know, how fast it's going over that distance. So for high energy particles, we use what's called the DEDX versus residual energy methodology, which is basically you have a stack of silicon, and it relies on the fact that if a particle goes through a material, it will eventually stop and come to rest, and it gives off a certain amount of energy. So if you have layers, sometimes it'll go, if you have a layer that's thin enough and the particle's energetic enough, it'll go through the first layer and give off a certain amount of energy, but then it'll continue through the next layer and eventually stop. And so if you put a whole bunch of these layers together and you measure the energy that the particle gives off at each different layer until it stops, then you can add up all these pieces of energy and then its final energy that it gives out. And what you end up is these traces, where things are grouped according to their nuclear charge, or Z. And then within that little trace, they're also slightly separated by their mass. And so you can now say, okay, these are boron particles, these are carbon particles, nitrogen, oxygen, and so forth. And so this is a common methodology that we use for a lot of spacecraft. Generally, if it's above a few MeV per nucleon, this is the methodology that's being used in these spacecraft. Okay, so as I mentioned, as everybody knows, they're associated with solar flares. And they're also, we measure those. You've seen data like that, where this is the X-rays that are measured from those types of things. So we have real-time data of these X-rays that go up. They're also associated with coronal mass ejections, which we have real-time data, as you've looked at, from SOHO and a bunch of other spacecraft. And you can see the different, this is a really fast, long-running movie, but you can see there's coronal mass ejections going off all the time, including straight at us. And so these are, and there's the solar energetic particles arriving. They're also associated with radio bursts. So these are also things that we have information on a regular basis. And this can tell, this is radio emission that's given off primarily from electrons. And there's different types of these. You have ones that come down very fast. You have ones that drift a little more slowly. This is frequency versus time. This is also interpreted if you have a density model in terms of distance from the sun, close to the sun up here, farther from the sun down here. And this can kind of, you can interpret this in terms of how fast those particles are moving. All this stuff can help us understand the acceleration of particles. I'm not going to be talking so much about solar flares accelerating particles directly, because we're talking about big events. So while the reconnection that happens in a solar flare and those X-rays can, the X-rays themselves don't do it, but that's what we see, that reconnection can accelerate particles. And so we can get SEP events just from solar flares if the conditions are right. But they're not generally the really big events. The really big events are accelerated by CME-driven shocks. And so you have a CME that plows through the material, the solar wind, creates a shock in front of it, and that shock is accelerating particles. Basically, you can think of it as the particles are scattering off of irregularities in the magnetic fields. And you'll hear more about this, I think, from Joe tomorrow. But and basically, this stuff is moving faster than this stuff. So these little scattering areas are converging. And so just like a ping pong ball going between two walls, if you bring those two walls closer together, that ping pong ball goes faster and faster and faster and faster. And eventually what happens is the energetic particles gain enough energies that they just escape. They just no longer scatter across these things. And so, but you can do that all along this shock, so you can create this whole spread of solar energetic particles over a very wide range, as opposed to a flare, which is going to happen in a very small area. So you can fill the heliosphere essentially with these energetic particles. Okay, so this is sort of how it goes. You start with, this is like the magnetogram that Nick was talking about earlier. So you have these active regions, right? And then maybe you get a flare, you know, one of these active regions erupts with a flare. This is the path I'm not going to talk as much about, but you can observe this flare in the X-rays, and then sometimes you can get energetic particles directly from that. More likely, and sometimes you don't. So there's a lot of times where this flares goes off and we don't see any energetic particles. Sometimes what happens is you have this flare that goes off and it drives a coronal mass ejection that you see, what we just talked about. And this creates a shock in front of it. And then that shock can accelerate particles and we get a solar energetic particle event, except sometimes it doesn't, and we don't get an energetic particle event. And the key is understanding these whole processes and what is going to end up in, you know, this case or this case. And that's sort of the whole thing about understanding how this stuff is accelerated and trying to predict it. And we're going to come back to that in a bit. So the problem is, because there's all these steps, solar energetic particle events vary dramatically in just about every way you can consider. So I'm going to just go over a few of them. So this is particles as a function of time. This is actually that October, November time period that I mentioned earlier. These are oxygen data. Each color is just a different energy, because we measure all these different energies. What you're seeing here at the top, these are all the flares that went off. So you can see there's, I don't know, 10 flares across the top here. And they're all X-class flares. There's actually M-class flares that went off. I think this X28 was one of the largest flares ever seen. These lines are when shocks actually pass the spacecraft. And you can see basically the shape of these things varies from event to event. Sometimes they're really small. Sometimes they last for a much longer time. Sometimes they are, and they also change with energy. Whoops, sorry. They are shorter at the higher energies, maybe longer at the lower energies. They peak sometimes when the shock goes by. Sometimes they peak earlier, depending on the energy, and so forth. So there's a whole zoo of stuff here. If we just look at the onset, the beginning of how fast those things come up, they are also all over the place. There was this event in January that is one of the fastest rising events. It basically would hit its peak within basically a half an hour of when the flare happened. More typical events like that event I just showed you is this brown one. So it looked really abrupt in those other pictures, but if you look at it in terms of hours, it's taking a while to try to reach its peak. And so whether the SEP event is going to reach its peak within half an hour, or several hours of that flare makes a difference if you're trying to warn an astronaut to come inside and take shelter. So that's something that we want to know. And they change with energy. If I integrate over those time periods, like, so if I look at any one of these events and I integrate over this time period to sort of see what the spectra is of the whole population of particles, how they're distributed in energy, you can see that their distributions are very different. Sometimes they almost always have a bend, but sometimes that bend is really strong. Sometimes it's higher energies, sometimes it's lower energies, sometimes it doesn't really want to bend at all. And you can get events like this where it bends here, but then it's really straight for a really long time, which means that you have a lot of particles at these very high energies. And that brings us back to the neutron monitors that I mentioned before. If you have enough of those really high energy particles interacting with the atmosphere, then you can get these signals in these neutron monitors, which are all over the Earth. And that basically, we call that a ground level enhancement event. It's still an SEP event, but basically what it's telling you is you just had an SEP event, or an SEP event is ongoing that has a lot of very high energy particles, and it's a very hard spectrum, and it's something that's a particular space weather concern.
Christina, you have a hand raise and a question in the chat. The first one was, what spacecraft was your X-class flare plot from?
So this was ACE, this one.
Yeah.
So the X1, those are, of course, GOES measure the X-rays. This is ACE. And the other question? Or hand raise?
There was a hand raise, or was that the question?
That was
okay.
That was me.
Okay. Great, thanks.
Okay. I'm sorry if I'm going through this fast. I'm looking at the time going, oh man. So anyway, we're going to keep going. So so these ground level enhancement events, these are sort of an extreme SEP event. So they're an extreme space weather concern. This is just what I said before. They tend to be much harder. This is the spectral index of this part of the spectra. And you can see that it's at, it's much harder than your average large SEP event. So this is a concern. Okay, it also depends on location. So if you have this CME that's coming right at you, you're more likely to see an event that's going to go up somewhat fast, but not super fast. It's probably going to last for a longer time across that top, and then it's going to decay. If it goes off to what's essentially your right, west, then it's going to go up really fast, but then it's going to decay, and it's probably not going to be as big. And this all has to do with how these Parker spiral field lines are connecting an observer to what part of the shock. So, and then of course that connection evolves as the shock moves out from the sun. If it's going off to your left, so it's what we call an eastern event, you're probably going to get a much more gradual rise, but it's going to peak basically when that shock passes you. So where you are and where the CME goes off makes a big difference in terms of the SEP event that you're going to see. And then a composition change. I'm going to hardly touch on this, but I'll just say that the composition changes all over the place. While it's mostly protons and helium, if this is just a measure of, these are just individual events, this is the total silicon fluence. So bigger events are up here, smaller events down here. And this is the composition, the number of iron particles to oxygen particles at a particular energy, and you can see that it varies by orders of magnitude. So if we want to know all that stuff, so here's the problem with forecasting these events, giving warning. Okay, so we want to know all these different things, how it varies, how fast it's going to go up, how big it's going to be, how long it's going to last, when it's going to arrive, all these things. And this is what we have to work with. And it seems like a lot. We have these great solar assets, right? So we can observe the X-rays, we can image the flare going off in all kinds of great detail. We have the LASCO and other imaging of the coronal mass ejection. We can measure how fast it's going. We have all these different spacecraft. This is actually a dated, we have more than this now. All these different spacecraft all over the place that NASA as well as ESA have put out there to measure all kinds of things. And so you would think we have lots of ways of measuring this stuff. So here's my next poll that you guys can stamp. Which one of these things or multiples of things do you think is going to be the best predictor? So if you had to pick one or two things that are going to give you the best indication of either whether you're going to have an SCP event or how big it's going to be, let's say, which one of these things would you think is the critical thing to actually measure? How fast the solar wind is going, how big the flare was, let's say in X-rays, where the active region was relative to your spacecraft, how fast the CME is going. I haven't really touched on this, but the super thermal ions are what's being accelerated by the CME driven shock. And so maybe if you have more of those, maybe you get a bigger event. And the direction of the CME, you know, is it going, that's sort of related to the location of the active region, but it could also go south a little bit or north a little bit, or, you know, not exactly straight at you. So I'm seeing lots of people that like the direction of the CME, flare size a little bit. Let's see if it slows down here. Nobody seems to care too much about the solar wind speed. Okay, great. So I know I have a few more minutes, so we're going to go and talk about sort of each one of these. And I don't know if I can erase these things or not. The last time I did this, I sort of lost my cursor. But anyway, there we go. Let's clear these. Okay. So so basically CME speed, that's one of the first things that lots of people said, you know, of course, it's driven by the CME. CME is going faster, going to get a bigger event. Well, that is true. They are correlated. So this is the size, basically the peak intensity of the event as a function of speed that were done were a couple of different energies. And you can see they're correlated. The problem is that if you pick a given speed, say you've got a 1,000 km/s CME going off, your prediction, if you're just following this line, can be, you can get an SEP event that's going to differ by 4 orders of magnitude in size. So if you tell an astronaut, well, it might be this big, but it might be 4 orders of magnitude higher, the astronaut's not really going to find that very helpful. And I can tell you the FAA is going to hate that. So, so the question is, are there other predictors? Well, we've looked at X-ray intensity, and yes, again, they're correlated, but if you have a given X-ray intensity, you still have several orders of magnitude difference in terms of the SEP event. Distance from the active region. So this we talked about a little bit in terms of the Parker spiral. So if your spacecraft is sitting here, this is Earth, for a typical solar wind speed of 400, you're usually connected over here around 50 or 60 solar longitude. And if that CME or the active region is located here, probably going to send off a CME this way. And this angle here is what's plotted here. You can see, yeah, it peaks around what we call best connection. But again, there's a big difference in terms of, you know, you can still get very big events over here if you're not well connected. Even if you're well connected, sometimes it's a very small event. So that doesn't seem to be a great predictor. the density of the superthermal ions, it is related, but it doesn't seem to be correlated. So this is looking at the size of the event as a function of the density of, in this case, iron the day before, assuming that's a proxy for this superthermal ions back to the sun, which isn't a whole nother thing. And basically it sort of puts a cap on it that says if you have a certain density, you're not going to get an event bigger than this, but still you can get a variety of many orders of magnitude. So this is part of the problem, is that we have all these assets, but no one parameter really tells us, gives us a good prediction. And I should have mentioned the solar wind speed actually does play a role. I didn't have a figure for this, but if the density of the solar, if you have slow or fast solar wind, that's going to affect that CME driven shock and how strong it is in its parameters, which affects the SEPs you get. And so while this looks really great, one of the things you have to keep in mind is this is not to scale, right? So what you're really looking at is all these assets are, and I apologize, this is American centric, but these are basically are all sitting, Earth is sitting basically here over in California, near where I am. And all these assets are maybe as far as the edge of the beach, whereas the sun is over in Hawaii. And so you can see what's going over in Hawaii with these great binoculars or something we have, but I can't measure what's going on in Hawaii. And I don't know what's going on in this huge region as all these SEPs propagate until I measure them over here. And so that's the big problem. And there's all kinds of things that happen in that region. And I'm not going to be able to go over most of these, but there's basically transport effects. You can inject one particular energy at the sun, and it's going to lose all kinds of energy and create a distribution of particles that you see at 1 AU. Interplanetary structures, if you have a CME ahead of the CME or stream-stream interaction, that's going to cause these weird effects in terms of what you see in terms of the particle intensity. And of course, all this stuff is changing, right? We talked about this before about if you have the CME, as it goes out, drives that shock, that CME is slowing down, that shock parameters are changing, what they're running into changes, the background solar wind is not the same, all that stuff is affecting all this empty space that we don't have any measurements of. And of course, the seed population, as I mentioned earlier, this is not a really good example of it, but basically what's happening in here and what's contributing, and that can even be old SEP material that's still kind of bouncing around and has lost energy, contributes to that. So that all changes. And of course, this is this whole problem that Nick brought up earlier, where we start all this stuff with a synoptic map, and we're really just measuring in real time this, and we're guessing at how all this stuff is evolving. So we don't really know what any of those measurements are until they come back around. So really understanding all these different pieces is very difficult, because most of this stuff that we observe is really close to the sun, and there's a lot of stuff that happens until you get here. And you need to be able to tell people whether you're going to have this kind of effect or whether you're going to have this kind of effect based on this stuff. And if you wait until you see the shock, you have a better chance at predicting that, but you've lost a bunch of time, right? Because you have to observe the CME, and you have to observe the CME and guess whether you're going to have a shock, or you have to observe the flare and guess whether you're going to have a CME and what speed it is, or ultimately what you really want to do is, and you don't know whether any of these things are happening, and what you really want to do is just start with this guy and predict whether you're going to have this. And this is what we call an all clear forecast, is at a minimum, can you tell me that nothing's going to happen for the next several days, so I don't have to worry about it. Turns out just even predicting nothing is really, really hard, especially if this is the only thing you have to work with and you don't know the chances of all those other things happening. Okay, so I'm almost done. I just want to mention two new assets that are trying to fill in that gap. One is Parker Solar Probe. It has a bunch of instruments on it. This is the energetic particle instrument suite. This is measuring magnetic fields, electric fields, and radio. This is measuring all the plasma stuff, and this is a coronagraph. And of course, it is now breaking all kinds of records. It's going in very close to the sun. It's currently at, well, it's not currently at, but its closest approach is currently 13.6, I think, solar radii. So it's really in very close. So you can think of it as, instead of being way out here, I've now taken this spacecraft and I've put it all the way over here. And so now I've actually been able to make measurements in this big gap. The other guy that's coming up is Solar Orbiter. Was launched in 2020. They aren't going in as close, but they eventually will go out of the ecliptic plane, which is what's being shown here. They not only have all these other same instruments like the energetic particle detector, magnetometer, and solar wind and radio, but they also have imaging. They have extreme ultraviolet, they have a couple of coronagraphs, they have a magnetogram, which is something that we were talking about the importance of, and they have an X-ray monitor, so they can actually see the X-rays as well. So these are new assets that are helping us fill in that gap and improve all our space weather forecasting. And I apologize for going a little over time, but that's what I have.
Great, thanks, Christina. That was a whirlwind tour.
I know, I'm sorry.
Oh, no, it was great, and it generated a lot of conversation. Mark has been handling some questions in the chat. There was a heated, I won't say heated, there was an active exchange on whether magnetic shielding on spacecraft would be valuable or not, and how much energy you might need to stop any SEPs. Let's see. We've got a couple of other questions that maybe. So one is, do SEPs impact the magnetosphere or the ionosphere?
Sure. So yeah, they do, and they can cause problems with the ionosphere, but they can also lose energy and help populate the radiation belts and cause all kinds of things that are just sort of sitting there, and those cause problems. You know, we no longer think of them as SEPs anymore, but they contribute to the environment in the magnetosphere that is causing other problems for other spacecraft. And of course, you have to think about all this stuff is sort of happening at the same time, right? So the CME that's accelerating these particles and the X-ray that is usually related to the CME, those things are all and the SEPs, they're all affecting the Earth, and then the CME arrives and it also affects Earth. So all this stuff is all happening at the same time. So it's sort of like when you're down, you're being kicked over and over and over again by a bunch of stuff.
If I might add to that a little bit, just one of the things to keep in mind is that radiation belt particles and SEPs, while each individual particle is high energy, compared to the plasma density, they're really low. So keep in mind that the SEPs are told where to go by whatever the plasma magnetic field is doing, and don't necessarily push on the magnetosphere. But
yeah, so the other thing that's kind of an interesting effect is, so you can have SEPs that come down over the poles, right, where the field lines are basically open. When you have a CME hit, it reconnects a bunch of those field lines, and so now you have even more field lines at the pole that are open. And so that's what we call a geomagnetic cutoff, is that magnetic field lines shield some of the SEPs up to a certain energy. But if you now squish that, and so you have a bigger range at the top where these magnetic field lines are open, now you get more and more SEPs coming over a bigger range. So that's also another, combination effect that happens.
Right, great. I think we should move into our break and office hours period. And we can take any further questions from either Christina's talk or my talk, and I'll answer them as best I can. And or take a lunch break or a meal break, shall I say, and be back for Mark Cheung at 11:30 Mountain Time. If I've got that, wait? Hang on, nope. 10:30 Mountain Time, right? Okay, thank you. Yeah, okay, and so whatever that is, your local time. So approximately a half an hour from now. All right. So Christine and I will be around for questions, and there's a bunch of there's continues to be a lively discussion in the chat. So we can go into the chat and sort of roll back and look at what's been going on there.
Yeah. I'll try and scroll back and see if there's any unanswered questions, but if people feel like they're, they asked something a while ago and it's been kind of lost, feel free to post it again. I'll try and answer it.
So I would say getting some Yeah, we're getting a lot of thumbs up. All right. And some cameras turned on, so I think we're ready. Christina, do you want to introduce Mark?
Sure. So Mark Cheung is going to be our first lecturer. He's going to start with, we're going to start at the sun and move out over the next 2 weeks. So Mark's going to do the solar data part. As you guys know, we've kind of had a data and a modeling part to each thing. So he's going to sort of go around and explain all this data. He works at Lockheed Martin in California, and he does a lot of outreach stuff. So I'm sure this will all be great. He's very highly experienced in analyzing all the gory detail of all these images that you've seen, as well as some modeling stuff. So Mark, why don't you go ahead? And I will try and interrupt you if I see some good questions in the chat. So people should continue to put those in there.
Great. Thank you, Christina. And thanks, Nick. And thank you to all the organizers of this this year's summer school. It is a great pleasure to be presenting to you some of the beautiful solar data that all the NASA missions and NSF observatories and also international observatories are collecting about the sun. This will be a tour mainly of the different types of data that we get, focused on the different layers of the sun. And feel free to interrupt me anytime you want. And the goal of this lecture, these two lectures, is not necessarily to teach you all the basic physics. So the take-home messages will not be like this equation is super important. You need to know this about the plasma physics. You get lectures about that tomorrow and also the rest of the week, I think. But it's important to know how the sun looks like. So let's start. All right. By the way, these are movies from the Solar Dynamics Observatory, and I'll explain that a little bit more. Okay, so very often in heliophysics, we think of the sun as this kid or monster, gives temper tantrums, gives out eruptions, creates a terrible space weather, and cause problems for our satellites, for our electric grids, all that stuff. You probably heard about that. I would like to present the sun from the astronomy perspective, studying the sun as an astronomical object, a beautiful one. So let's go and talk about what are the most salient observational facts about the sun. All right. It's been mentioned several times. It rotates, but not as a solid body. The equator rotates faster than the poles. And the sun also differentially rotates with respect to the radial distance from the solar interior, from the center of the sun. And the way we know this is to use helioseismology. I'm not going to go too much about helioseismology, but I'll show the data that is used for these purposes later. There are sunspots, and the number of sunspots waxes and wanes with an 11-year cycle. And the magnetic fields are not just in the sunspots, they're everywhere on the sun. They're inside sunspots, there's the strongest there. They're also at the periphery of sunspots. There's sunspots, and then what's around the sunspot, that's called an active region. It's a whole complex of magnetic fields. But even outside of active regions, there are still magnetic fields everywhere on the sun. The sun is a panchromatic astrophysical object. What do I mean by that? What I mean by that is that in all the electromagnetic spectrum, if you observe the sun from gamma rays to X-rays, UV, visible, infrared to the radio, you'll see that the sun emits something. So this is an example of a composite spectrum of the sun, because most of the energy is peaked around the visible wavelengths and infrared wavelengths. That carries most of the energy that the sun emits, but there's radiation from the sun everywhere. And the variability is particularly high in the X-ray and the radio ranges and the UV. So let me show you. So in terms of the amount of radiation measured as an irradiance in units of ergs per square centimeter per second per wavelength per micron here, there's orders of magnitude. There's about from 10 to the 6 to 10 to the minus 18, 20 something or so orders of magnitude in terms of the irradiance from the sun, but it emits in all these wavelengths. And in this case, we're looking at the radio here, the radio end. You'll see that there are different components. There are some slowly varying components called the S components. And then there are sometimes large bursts from the sun. And also, when you have a large burst, the radio spectral irradiance can increase by a few orders of magnitude. The same with the UV and X-rays and gamma rays. Okay. So it's a panchromatic object. That's fine looking at it in terms of a plot like that, but let's try to put it in more intuitive terms. Okay, you go from gamma rays to radio. The order is reversed from left to right now, and over this range, huge range of length scales, in terms of the lambda, the wavelength, the sun is emitting. It's emitting gamma rays that are, the size of nuclei. It's also emitting radio waves the size of buildings. So that's very interesting. And what we would like to know is why does the sun emit over all these wavelengths? Well, the main part that carries the energy, you can roughly model it as something like a black body spectrum for a surface temperature of the sun, which is about 5,800 Kelvin. But then actually, if you look in very detail, if you zoom in, there's actually a lot of spectral lines. So to a very rough approximation, you can model the sun as a black body at emitting at a certain temperature or a few thousand Kelvin, but it's much more complicated than that. Okay, so now the hot corona consists of magnetic loops that are anchored at or near sunspots. That will be very obvious when we look at the coronal images. And then one thing that I do want to point out is that total eclipses are awesome. Partial eclipses, not really. And this is an image. This is a photograph, a highly processed one, of a total solar eclipse that happened in 2017 above Oregon. And you can see that in this image, around the moon, there are some reddish areas here hovering above the surface of the sun. Those are prominences, and this is chromospheric material that is at temperatures of about a few tens of thousands of Kelvin. And then there's the corona. The corona means crown, and you can see why it's named that way, because it looks like there are these helmet streamers, they're called, that are poking out like parts of a crown. This particular type of observation that you can see with your naked eye, without so much resolution, of course, is from the Thomson scattering of free electrons in the corona. And the upcoming mission, Punch, it's a NASA Small Explorer mission, will be measuring this scatter light in very high detail and sensitivity, and measuring the polarization states of this light. And from that, and with appropriate numerical modeling, you can infer the the structures of coronal mass ejections in terms of the morphology, in terms of even the direction that they're headed towards, because depending if they are heading towards the Earth or away from the Earth, the polarization state would be different, given the models that you have of coronal mass ejections. So that would be a very exciting mission. On the ground, if you do want to see an eclipse, I mean, I know you're all over the world, but if you happen to be in the States, there are 2 upcoming eclipses of note. There's the annular solar eclipse in 2023. Forget about that. I know I'm being pretty extreme here, but if you had to choose one, go to the total solar eclipse and choose a place that's sunny. Okay. The reason a total solar eclipse is so much more interesting, in my opinion, than a partial eclipse or an annular solar eclipse is because the white light corona is about 1 million times dimmer than the solar disk, than the light coming directly being emitted from the surface of the sun. And when you have a partial or annular eclipse, the part that is not occulted, that still dominates. And so the light scattered in the Earth's atmosphere from that unocculted part of the sun will still dominate, and you will not see the corona. So it just looks like part of the sun is occulted. But when the entire disk is occulted in a total solar eclipse, then you don't get that scattered light from the unocculted part of the sun, and you see this glorious crown. So that's why I generally don't encourage people to make a huge effort to go and see partial eclipses out of fear that they will not make the effort to go and see a total solar eclipse, which is awesome. Okay, so let's talk about the different layers of the sun. All right, so we have the core, where the temperature is very high. It's very dense, and you have a fusion there. And then above that, you have the radiative zone. And what the radiative zone is the region in the solar interior where the energy that's being produced in the core of the sun is primarily transported by photons. Photons scattering around, being absorbed and then re-emitted, bouncing around. And within this region, it could take a very, very long time, on the order of 100,000 years or so for light to actually diffuse through this random walk process to the convection zone. So the outer convective envelope of the sun, this is still considered part of the solar interior. The convection zone is where the opacities are sufficiently strong at these particular temperatures, such that it's easier for the energy to be transported by motion. So you have a blob of plasma, which when perturbed upwards, it becomes more buoyant than its surroundings, and then it continues its motion upwards. So that's called the convection zone. And in this region, the energy is carried by convective flows. And then once we reach the photosphere, it's where the plasma becomes transparent again. So then the mode of energy transport changes again. The blob of plasma in the solar interior, when it reaches the photosphere, suddenly sees the universe and radiates out its energy in terms of photons. You can model that as a black body spectrum of a few thousand Kelvin, and then that mode of transport, a lot of it does go into the visible and the IR, but also the convective flows, when they reach this layer, they also get diverted horizontally, and because of the presence of magnetic fields, they're coupled to the magnetic fields. They shuffle the magnetic fields around, and the magnetic field is able to carry that energy in the form of pointing flux into the higher layers. And it just happens that the sun is so stratified that when the magnetic field pokes through the solar interior, the densities in the solar corona are so low that the magnetic pressure dominates over the gas pressure. And so that's why the magnetic field becomes space filling in the solar corona. You find that in this particular figure, there's no mention of the chromosphere. In fact, in a lot of talks in heliophysics, you might hear about the photosphere, you might hear about the solar interior and the corona, but not the chromosphere. But we'll talk about that. Nick already mentioned how we measure magnetic fields. So I'll just recap a little bit. This is a movie of the sun's magnetic field from the Solar Dynamics Observatory. You can see that the sun is rotating. You can also see that the magnetic field is not just within sunspots. So for example, this is a sunspot. This entire patch here that includes the sunspot is a so-called active region. You can see that at the periphery of the sunspot, there are flows. There are little magnetic patches flowing out. Those are called moving magnetic features. And one of the common things you'll find is that usually these magnetic patches in active regions, they have opposite polarities. There's one polarity which is leading, meaning that following the direction of the rotation, it's in front, and then the other is trailing. And typically, not always, the leading polarity sunspot is more compact and coherent than the trailing one. And modelers use these clues about the asymmetries of the sunspot groups to determine what might be the interior structure of the magnetic fields that cause these sunspots. But you can imagine that this positive and negative polarity, you can just imagine maybe a little loop, an omega, so-called omega loop that used to be submerged, and then as it pops through the solar surface, when you observe at a cross-section, then you'll see that one part has magnetic field going out of the sun, the other part has magnetic field going into the sun. So that's how you can interpret these opposite polarity patches. Okay. And then outside these active regions, there are these fields here. For example, you can see a network of magnetic field. Each of these cells is called a supergranule. They're about 30,000 kilometers big. There's a spectrum of sizes. And it remains to this day a mystery as to what is the physical process or combination of physical processes that lead to this apparent special scale. The convective scale at the very surface of the sun are the granules. It's about 1,000 kilometers. That is determined by the balance between how much energy there's a blob of plasma carrying and how quickly it irradiates out into space. But this is a much bigger scale, and it remains a mystery why we have supergranules. Okay. So Nick already mentioned that Hale was the first to measure magnetic fields using the Zeeman effect. And it was an extremely remarkable achievement to use the newly invented quantum mechanics. Actually, at the time he wrote this, I'm not even sure that the full quantum mechanical description of the Zeeman effect was even developed yet. There is a classical way to explain it, but he looked at the splitting of the lines and found that there is magnetic field in one sunspot and then opposite magnetic field somewhere else, and then suddenly the sun as an astrophysical object became a magnetic object, and that changes everything. Nowadays, we have very high resolution observations of sunspots. You can see the umbra. This is, by the way, a visible continuum or Fraunhofer G-band movie from the Swedish Solar Telescope. You have the penumbra, you have the umbra, and these days people tend to mention Tesla a lot. So you can use Tesla as a unit. That's the same as 10 to the 4 Gauss. So the umbra is about 3,000 Gauss. The penumbra is weaker, and the penumbral field tends to be horizontal. And you don't see it from this image, how it's measured, but you use the same effect to do so. Now, each of these granules, I talked about granules before, they're the convective flows at the surface of the sun. They're about 1,000 or so kilometers wide. So they're like the size of states in the United States, pretty big. And they come and go in about 10-20 minutes. But a sunspot is much more stable.
Mark, can I interrupt you for just a second?
Yes.
So we have one question related to this particular thing, so we'll start with that, which is why does the umbra appear darker in comparison to the granules around it? And then there was a earlier question about how we get information from the sun's interior, like how do we estimate the radius of the sun's core?
Okay, so the second question, or the interior question first. So we get information about the sun's interior using a combination of observations and modeling. And the way you model stars in general is that you have an equation of state for the stellar material. It depends on what you think is in the star, like how much metallicity it has. Okay, and then you consider its mass. You have these stellar evolution models that basically solve for a star that is in hydrostatic equilibrium, and transports energy either using radiation or convection, and whether it transports by convection or not depends on the temperature gradients. So that's all from the equation of state. That's a way to model it. But to confirm whether your model is correct, then you use helioseismology, and helioseismology allows you to probe how the sun is stratified in the interior, but also how it rotates. And you also use neutrinos. So you use neutrino oscillations to confirm whether your theory of how fusion occurs is correct. And so that's one of the major achievements in the last century, is to use solar neutrinos. Okay, so the other question is, why does the umbra appear darker in comparison? So that's a great question. I think Herschel thought that the umbra was an opening into the interior of the sun, and that he was convinced that you could see like people and houses through this opening. I'm paraphrasing, but it wasn't clear. But once Hale discovered that there are strong magnetic fields, very strong magnetic fields. How strong are they? I mean, they're basically the strength of magnetic fields that you would use in magnetic resonance imaging machines. You know that if you go take an MRI, you don't want any metals on you. Very strong fields. Now, what happens is people like Chandrasekhar looked at the influence of magnetic fields on convection and discovered that the strong magnetic fields will inhibit convective flows. So it will inhibit how easily the plasma can move through the layers because of the strong magnetic field, and that affects the amount of energy transport by these convective flows. And as a result, there is a suppressed amount of luminosity through sunspots. Yes, okay. So how do we measure these magnetic fields? How did Hale do it? Okay, so think of you know, when you go to the 3D movie, it's not really common these days to go to 3D movies, but when you go to real 3D, so there are two different technologies. One was that the glasses one had they had like linear polarization of different orientations. But then when you go to the 3D movie and then you tilt your head, then your images are now like a double image. So that's not a very good technology. Another type of technology they use in these 3D movies is to have a circular polarization. So you might have left circularly polarized light going through one lens, and then the opposite circularly polarized light going through the other one. And then your brain will add those two images, and then you get this 3D impression in your head. So yeah, this is what you do in the 3D movie. But now if you took those two images and took the difference, so yeah, left minus right, and it was at a wavelength where there's the magnetically sensitive line forming. The difference between those two images would be this. Yes, so Mark was pointing out that Hale was using the total intensity. When you have very strong fields, you don't need the polarization states because the line splits into three clear components. These days, in order to have a higher sensitivity to the magnetic field, and also to look at to decompose the magnetic field into the horizontal and vertical components, people tend to use polarization. So actually, when SDO was being commissioned and the pipeline for creating the magnetograms was not ready yet, I was a bit impatient, and I just loaded a couple of images. They sort of look like this, and then I took the difference, and then I got something that looks like, oops, sorry, let me go back to something that looks like a magnetogram. So that was a whole person's magnetogram and not quantitatively accurate, but that's sort of how it's done. So if you want to know,
Mark, sorry,
Yep.
Pratik had his hand raised. I don't know whether Pratik, your question had been answered. It took a little while. I think it was off sequence there.
oh, corresponding to, why don't we see dark patches for all active regions? Okay, so
Yes.
so active regions can evolve. Usually when they are emerging, they start off with smaller scale fields, and the strength of those fields might be 1 kilogauss instead of 3 kilogauss, and they might be distributed over a wide area. And magnetic fields at those strengths are not enough to really inhibit the convection to the extent that it would cause a darkening. When the magnetic field gathers together into a big conglomerate and becomes 3,000 Gauss or so, then they can inhibit the magnetic field. So
Sorry, Mark, for interrupting. I'm just doing running commentary.
okay.
I was showing all the...
Yeah, SDO data operations cost 100 million US to set up. Yeah, it depends on how you count. I mean, the mission is almost $1 billion class mission. So yeah, it depends on how you count. If you attribute the certain parts to just the data system, yeah, it takes a lot of people to make these instruments work. So if you took linear polarized light and made these various combinations, you get the Stokes IQU parameters. If you took the difference between the circularly polarized light, you get this, the V. Now, when you solve for the radiative transfer of light through a population of atoms sitting in a magnetic field of a certain strength and orientation, then you can predict and model how these Stokes profiles will look like. I can only find a low resolution version of this movie from Juan Manuel Borrero. He made this for his PhD thesis, which then also was included in his living reviews in solar physics. The x-axis here for all these plots is wavelength measured from the center of the line. And so if you had no magnetic field, and doesn't matter what the inclination or azimuth angle is, this is how a magnetically sensitive spectral line would look like. If you start to increase the magnetic field strength, you will see that the line starts to split. Eventually, yeah, okay. Okay, if you keep on going to like 3000 Gauss, then you would see like a really strong 3 components. Here, he only goes up to 1500 Gauss, and then we're assuming that the person is looking down. So the inclination angle is 0 at the moment for the magnetic field. Now, if you tilt the magnetic field, then you start to see the linear polarization coming in. Before that, when the magnetic field was purely along the line of sight, there was no linear polarization. The Q and U were 0. But the Stokes V looks like this. So if you tilt the magnetic field, then you start seeing the Q and U. If you rotate the magnetic field also in the plane of the sky, you get a transfer of the Q signal to the U signal, because Q and U measures different senses of the linear polarization in the plane of the sky. And so by having these models and by measuring these profiles is how we measure the magnetic field, not just the line of sight components, but also the components in the plane of the sky. So this is a scan. Hinode is a Japanese, US, and European mission that was launched in 2006 and has a spectrograph that not only takes spectra, but also measures the polarization states, and it scans through an active region. So it has pretty decent resolution and very high sensitivity. The continuum signal, meaning that the brightness outside of the line, outside the spectral line, looks like this. So you see the sunspot, you see light bridges inside sunspots, you see the penumbra. It's a beautiful observation. When
Mark,
you,
I think so. This might be a question related to sort of that resolution that you're talking about. If I understand Jakob's question, he's saying, how far should the distance be between the active and passive region? I assume he means so you can tell the difference.
How far should the distance be between the active and the passive region?
Jakob, if you want to unmute yourself and try to
Okay.
explain your question a little bit more, that would help too.
Yeah, Jakob, do you want to clarify what you're asking?
Yeah, so I just want to know what should be the distance between the active, because I know the active sunspots region is always located at the poles. Am I correct or not? So, and sorry, the equatorial region is where we find the passive region, I think, for the sunspot, right?
Christina, did you understand? Trying to parse that.
Yeah. So Jakob, were you talking about the difference between the poles and the equator? The active regions are mostly going to show up near the equator.
Okay.
Yeah, the active regions they in a butterfly diagram. So in like the synoptic maps, if you then stack them in time, you'll see that they first appear at mid latitudes and then they migrate to lower latitudes as the solar cycle progresses. If we didn't answer your question, write me on Slack and then we can have a conversation. So this is the line of sight components of the magnetic field. From what one does is you measure, let's say at a certain pixel, you have all 4 Stokes profiles, and then you have a iterative algorithm which estimates, guesses in an educated way what the magnetic field strength is, what the inclination angle and the azimuthal angle are, and also actually the gradients of the source function, how quickly the temperature drops as a function of optical depth. And then you can find the set of parameters that best fits these spectra. And so this is how these maps are made. And so you can see the opposite polarities of the sunspot group, but there's also a lot of mixed polarity, and you can see the fine filamentary structures in the penumbra. So that's the line of sight component. But because we have the linear polarization, you can also get the transverse components. Transverse meaning in the plane of the sky. But the problem is that the IQUV profiles for a certain azimuth angle are identical to the profiles when the azimuth angle has been rotated by 180 degrees. So the Q and U profile, So the Q and U profile here for 30 degrees azimuth exactly, actually IQU, all of them, all these profiles are the same when the azimuth is 210 degrees in the plane of the sky. So this is called the 180 degree ambiguity problem. It is a fundamental limitation of using the Seymour effects to measure magnetic fields. We can get the sign of the magnetic field for the line of sight component, but there is this ambiguity for the transverse field. And so one needs to make additional assumptions in order to resolve this ambiguity. And there are codes for that. The SDO HMI data pipeline does resolve this ambiguity. And the quality of this resolution is tested on test cases, but we don't really have for every part of the sun the ground truth. So it's model dependent. But then with HMI, HMI doesn't have the spectral resolution that the Hinode instruments have. It only measures 6 wavelength positions, but it looks at the full disk all the time, and you can get the vector magnetograms at 12-minute cadence, whereas Hinode takes more than half an hour to scan a big active region. So that's the benefit of having HMI. You get these vector magnetic fields showing you how magnetic fields, sunspots develop, and how the magnetic field at the surface is being twisted up into regions that are amenable to creating eruptions and flares. So just want to do a time check. I guess I have how many minutes more before the break? Okay, 10 minutes more. Okay, good.
Yeah, 10.
Okay, so that was the photosphere. Now we're going to go to the chromosphere. Okay, so above the photosphere, we have a lot of different types of observations that allow us to probe different parts of the atmosphere. So consider the right-hand side here. This x-axis is height above the solar surface, okay, in kilometers. So this goes to about 2.5 megameters. So consider this is the surface. Based on observations from different instruments on board orbiting observatories in space, as well as sounding rockets, I think, over many years in the 70s, Vanazza, Everett, and Loza modeled what might be an average stratification for the solar atmosphere. So from the solar surface, there is a decrease in the temperature. And then at about 500 kilometers, it's what is called the temperature minimum in these sort of models. But then it gets hot again. It gets hotter and hotter and hotter, and then it gets really hot. And then above this region, we get the corona. So the question is, why does it get hot again? Now, but let's talk about that later. The important thing here to note is that there is such a wide variety of observations that are used to constrain the solar atmosphere. You have the H alpha lines, the H alpha invisible. That's the Balmer series. H alpha has beautiful images of filaments, and it forms over a wide range of heights. When you look at the H alpha core, it's actually pretty high up, but then the wings are near the surface. And then in the chromosphere here, we also have the magnesium. There's the H and K lines, but let's look at the K for the time being. There's the magnesium line in the UV. There's the calcium line also, and in the visible, and these also are formed over a wide range of heights. The radio, why do I keep on doing this? Sorry. The radio observations and millimeter observations will allow you to probe deeper and deeper into the atmosphere. From your basic plasma physics, you know that there's a certain plasma frequency. In order for the EM waves to propagate through a plasma of a certain density, that frequency needs to be above that plasma frequency. It's related to the square root of the electron density. So you need higher frequencies, shorter wavelength radiation to probe deeper and deeper into the atmosphere. There are other lines that are in the UV that can be used to probe this region. I won't talk about this. There's a Lyman alpha, which is also a very strong line. And depending on whether you're looking at the center of the line or the wings of the line, so this one means at 5 angstroms away from the center of the line, you're also probing different regions. So combining all of this and including all the atomic physics, they created this profile of the temperature. So it's a landmark paper. You'll sure come across it if you're studying the solar atmosphere. Now, there's a Living Reviews article by Joris Lennertz about radiation hydrodynamics in the solar atmosphere, and taking a model like the one before, you can go and can solve the atomic physics, for example, just like they did, and you can consider the net radiative cooling rate from different lines. This is a very complicated plot, but the important thing is that in this height, this chromospheric height range, basically the radiative cooling is dominated by spectral lines, and the calcium 2 lines, magnesium 2 lines, and then higher above is the Lyman alpha line. So magnesium 2 and Lyman alpha, you basically need to observe from space because it's UV. So that's one reason why we like going into space, in order to measure these things. So let's see. There's a famous paper about solar tornadoes that made the cover of Nature by Wedemeyer Bohm. And what they did was that they used different observations to study some magnetic vortices at the photosphere and how they appear higher up in the chromosphere as well as in the base of the corona, using different measurements. And they found that there's some twisting going on. These vortices at the photosphere that are generated by granules flowing into each other, and when they converge, you have this vorticity generated. And since there's magnetic field there, it's basically spinning the magnetic field into these tornadoes. These things are tiny. They are at the scale of at most a few hundred kilometers horizontally. So this nature cover is completely misleading. It looks like a tornado that's the size of the sun, but this is just really blown up. Okay, they're really tiny things, but they're everywhere. And so the idea is that all this twisting motion, dragging magnetic field around, creates a mechanism that will transfer the energy that used to be in the convective flows and channel them into the upper atmosphere, including the corona. And Sven Wedemeyer Bohm has also a review paper that is very famous. This figure is from that review paper, showing all the things that might be happening from the photosphere to the chromosphere and then to the corona. And so if you go to a talk that doesn't mention the chromosphere, one reason is that maybe it's too complicated. So usually it's just considered a boundary condition, or just you don't think about it. But when you do study it, it's really interesting. I have about 2 minutes before the breaks, so I'll try to confuse you a little bit. So underneath this surface is the convection zone, and then you have all these convective flows running around. The convective flows and the convection zone have generate actually oscillations. There's a resonant cavity in the convection zone, and you get this preferred power in certain wave modes. These are called P modes and G modes. And the convective flows and these waves, they sort of act on whatever magnetic field is poking out. And then also the convective flows, you know, when they overturn, they can fold magnetic fields. And when you fold magnetic fields, you can have these current sheets. This is about a supergranule. At the edge of the supergranule are these network fields that I shown before in the magnetogram. These are stronger fields, so they expand further up, and they might expand far enough that they can show up in the extrapolations of the field to the corona. And in fact, this structuring is being invoked to explain the structure of some of the solar wind in situ measurements from Parker Solar Probe. But one important thing is that none of this is static, all of it is dynamic, and I'll show some movies of that after the break. Okay, so are there questions before we break?
I don't see any in the chat. If anybody wants to add something or raise their hand, or you can take the next 10 minutes to think about it, and we can do another quick poll before you get started in 10 minutes, Mark.
Yes, I will leave this screen on, and feel free to annotate this, or you
Yeah,
like?
because it doesn't have enough things on it already.
Right. Okay, see you all in 10 minutes.
10 minutes. Great. Thanks, Mark.
Where are the tornadoes?
Right, this paper is old. It was before.
Okay.
Okay, there's a question. Are the sunspots related to supergranular formation edges? So the supergranule is most clearly seen in magnetograms and in continuum images that have bright points in those intergranular lanes between supergranules. From following the movies of the magnetograms, what one finds is that generally when you have an active region decaying, the magnetic flux from the decaying active region spreads around and they get collected into the supergranular edges. I wouldn't call them supergranular formation edges because we don't exactly know how supergranules form. But yeah, so in terms of the magnetic flux being a tracer of supergranular edges, yes, they come from active regions. Since I'm talking about supergranules, the problem with our theory of turbulence convection is that when you do numerical simulations of all this convection, you can simulate a small part of the surface and it actually looks pretty much like observations. But then if you expand the computational domain to be big enough that you should see supergranules form, we have a problem. When you look at the spatial power spectrum, how much convective power there is at a certain spatial scale, then at the scales of the supergranule and larger, so scales larger than 20, 30,000 kilometers, there is too much power at those large scales in the simulations compared to the power that we measure from the sun. So for some reason, the simulations are creating these large scale flows with a lot of power that don't exist on the sun. So there's no special scale in the simulations that correspond to the supergranular scale. A potential resolution to that might be that when you include the magnetic fields, at some point the convective flows are so efficient at generating the magnetic fields in this convective turbulent dynamo that the magnetic fields start to be important and they throttle the convective flows and suppress the power. But so far it doesn't explain everything yet. It doesn't decrease the power in the large scales enough to give supergranules. So it's a mystery.
And now the figure is updated for a new publication.
Yeah, they can write a new review paper. It's a very informative figure actually, and it's 2D. That's also partly why there are no vortices. So, Christina, should I begin? Or Nick?
All right, it's time. Nick, do you want to make sure everybody's here first?
Well, sure, and I would the only way to turn on your camera or give me a thumbs up. Great. Okay, we're getting lots of thumbs up, so I think we're good. And Joe
Okay.
Cohen has checked in.
Okay. All right, Mark, do you want to start off with answering the question that was that Raphael had?
Yes. So the question is, what is the meaning of the term fluctosphere? So you can see the cursor here. It says fluctosphere, and so that's not traditionally a term that was used to describe different layers of the atmosphere. Actually, I didn't really define what is the corona, what is the transition region, what is the photosphere. Well, I said the photosphere is where the mode of energy transfer goes from the convection to photons. So that's the photosphere basically. And that's usually when we observe things on the solar surface, that's what we mean. The chromosphere is more like a temperature range of 10,000 Gauss or so, 10,000 Kelvin or so, to tens of thousands of Kelvin. The corona is anything that is like 1,000,000 Kelvin or above, and then transition region is basically the temperature range between the chromosphere and the corona. The fluctosphere in this review paper is meant to describe the fact that in this region around the chromosphere of about 1 megameter or so, there tends to be a lot of shock waves going through. And when you look at how the optical depth level varies, it's fluctuating all the time. The reason there are these shock waves is because the atmosphere is stratified. There is a high density contrast, much lower densities below. And so when you have little wiggles at the photosphere, they send waves up. And due to the diminishing density, these waves shock. So you're sending shocks up all the time. And so the shocks change the temperature structure and change the layer at which, for certain spectral lines, optical depth unity, optical depth its unity. So that's basically why it's called the fluctosphere. Okay. And by the way, a very clever thing the authors did here was to put the reference in the figure itself. So whenever people show the figure, they would know where to find this. The problem is that after the paper was accepted, it only got published in 2009. So 2009 is the actual reference. So the IRIS mission, the interface region imaging spectrograph, is a UV instrument that measures what happens. Let me see. Is there a smudge here? Yeah, there are still the tornado smudges that I made before. So let me clear that. Clear. Oh, okay, clear. Okay, yeah, that's better. All right. It's a UV spectrograph. It measures the magnesium H and K lines and the magnesium triplets. So let's take a look. If you raster an active region with IRIS, and now you look at an image at a certain wavelength, in the wing of the magnesium K line, this is more like the top of the photosphere, maybe near the temperature minimum. It's quite low down. You see that there are these little cells. They are about the size of the granules, but the contrast is reversed from photospheric images. It's because there is this thing called the reverse granulation, whereas in the photosphere, the intergranular lanes are cooler than the granules. Above that, the temperature structure is reversed. That's called the reverse granulation. So this is why you see these little voids here. Now, if you then step through to the K line, wow. So when we scan through, we see that it appears that we're seeing higher and higher up. When we get to the core of the line, that's where the opacity is very strong, and you reveal that there are all these fibrils connecting large distances, and these are shaped by the magnetic field. The hypothesis is that these fibrils are aligned with the direction of the magnetic field, and numerical simulations and radiative transfer calculations do confirm that indeed they are tracing the directions generally of the magnetic field connecting different regions. So when you go from the wing of a spectral line, you usually see lower down in the atmosphere, and in the core where the opacity is high, you see these structures. Okay, now. Okay, now if we continue scanning, then we're going towards the wing again. So we're going and seeing the lower levels again. Okay. Now, if we continue scanning, then we see a different set of lines. Actually, this is a magnesium triplet. And there's a paper from the IRIS team that talks about how the magnesium triplet brightenings are signatures of lower atmospheric heating. So basically, we can use the magnesium H and K lines as well as the triplet to diagnose different levels of the atmosphere. It's very pretty. And then when you keep on rastering, this is a lower resolution raster, then you can see how active regions, this is an active region emerging. You can see that there are some brightenings here. You can see that the filaments are being pushed away, they're evolving as more and more field comes up. You can see some in the triplets. So these 4 panels are at these different wavelength positions illustrated by these white markers here, okay? So the right panel is in the magnesium triplet. The brightenings show you lower atmospheric heating. In the K line itself, you see the filaments, the arch filaments. And then in the wing, you see closer to the lower part of the chromosphere, the top of the photosphere. Okay. Now, so that's a space instrument because it's in the UV. Actually, IRIS also observes not just the near UV, but the far UV. And in the far UV, you have lines like silicon-4 and carbon-2, which are diagnosing the transition region, and not just the chromosphere. And now back to the ground. This is from the Swedish Solar Telescope again. And this is not H alpha, but it's H beta. So it's at around 480 nanometers. But it's in some qualitatively, it looks like H alpha. In the wing, this active region is not at the center, so it's more towards the limb. So you're sort of seeing it in projection. And when you see a active region in projection, other than seeing the penumbra here, you see that the granules look like they're almost like little hills. And in between the granules, where there is a magnetic field, maybe a few hundred Gauss or 1,000 Gauss, you see these brightenings. These are hot wars. The reason you see these hot wars is because the magnetic field, the presence of the magnetic field means there's a magnetic pressure, which means you need less plasma there to have horizontal pressure balance. And so it's evacuated. It's lower density, so you can see deeper. And when you see deeper, you get the brighter structures. So that's called a hot wall effect. Okay, so this is at 600 milliangstroms away from the core of the line.
Mark, you got another question from Miguel on the filaments.
The magnetic tubes seem to be different at different observation lines, right? The way the filaments appear depends on the spatial resolution you have, but it depends also on the spectral line you use, because it depends on where the opacity is. And the opacity depends on a number of things, not just the local temperature. In fact, a lot of the lines in the chromosphere do not form in so-called local thermodynamic equilibrium. They might depend on the history of how the plasma moved in the chromosphere and how it was heated. They also might depend on the radiation field from its surroundings, and so you have to take all of that into account. So you need to do very detailed calculations to get the opacity right, and so different lines will be sensitive to different effects. Okay, but this is in the wing. Okay, so we're seeing lower down, but if we play the movie, oops, oh no, if you play the movie, then sometimes you see these little filamentary structures. The reason you see these filamentary structures, even though you're far in the wing of the line, is because possibly because they're moving at speeds such that they're blue shifted, and so at this wavelength position there is still opacity, and so you can use these sort of signals to diagnose the Doppler velocities of filamentary material. When you go to the core, it looks like this. It's a little bit like the iris observation, the high resolution and extremely pretty. And this is a small flare that you see. So, and then maybe some of you can see that it seems like some of these, the tops of these filamentary structures are bobbling up and down. So they will be characteristic of a shock waves passing through. So that's why it's called the fluctosphere. Okay, so that's from the Swedish Solar Telescope. We have the Daniel K. Inoue Solar Telescope on Haleakala that has begun operations recently. It's a 4-meter class telescope. Beautiful engineering, and it seems to be working well with at least with the commissioning instrument. So this one is from the broadband imager instrument on DKIST, and you see in very high resolution not just the granules but also these brightenings, these bright points. They actually, you can see that they look like ribbons. It's just fascinating how much structure you see at the photosphere. And then you can check the movies out and see how these brightenings evolve. Now these things are bright. The models show that they're bright because there are patches of magnetic flux tubes and ribbons here that evacuate the plasma, and so you see deeper, and again that's why it's bright. Okay, so the radiative convection, magnetic convection simulations explain it that way. So on this slide, one image is a DKIST observation, and the other one is a synthetic image from a simulation. So I would like you to use the annotator tool to tell me which one, to just put a dot or something, which one is the real observation. I'll give you 20 seconds or so. Please annotate. I just want to see how good you are at telling which one is the observation. Okay. Interesting. Where's my cursor? Let me find my cursor. Oh, interesting. So it seems like there's probably more people voting for the right-hand image. Does anybody want to say why you think the right-hand image is the observation? Please unmute yourself if you want to say why. Okay, I'm sure.
I think it looks more similar to the one that you just showed.
Is there anything in particular?
Well, I was looking at the kind of the, I guess, shadows in the within the cells, the brighter cells. I think that the ones there's all this like smaller structure in the one on the left, and it looks different to me than the one that the image that you previously showed, in my opinion.
Yeah, that seems like a valid reason. Anybody who voted for the left image want to say why it looks like the observation?
I'm not sure which Dorcas was voting for, but they have a comment in the chat.
The left looks more. Wait, I'm trying to find my cursor, and I can't find it right now. Wait. Oh, now I can see it. Okay, so let me go back to that slide. Okay, so the left looks more patterned, and the right is more random. It could well be. The answer is that the right image is the observation, and then there might be many valid reasons for why one thinks the right one is the true one and the left one is the simulation. But for me, I see more structure in the brightenings in the real image. For example, in here, if you see my cursor, there's some dark parts inside the brightening that's you don't really see in the simulation. But I mean, you have to really look hard, and then these are on the same scale, brightness scale. So the simulations are doing a remarkable job, considering the simulation was performed in 2014, and now we have simulations that are finally catching up and telling us what's wrong with the simulations. So that's very exciting. All right, okay, now, okay, unfortunately, I will clear. I can't find my cursor again. Oh, clear all drawings. Okay, I don't know why it's so hard to find my cursor. When I press C, it still doesn't appear. Sorry.
We had the same problem earlier, so it's not you.
Yeah,
So
I had the same problem. I think it's when you annotate, then it suddenly confuses what's going on with your cursor.
So I can't even move forwards and backwards with the mouse or the keyboard right now.
I had the same problem. It does come back after you go past a slide or two. I had to go down to the corner.
But I can't even go. Oh, okay, right. All right. You know what? While I have this, let me close the annotator tool and come back. Okay, all right, got it. All right, so the coronal heating conundrum. So if we estimate how much energy there is available at the photosphere, we know the radiative flux at the photosphere. You can estimate that from the sun's luminosity, and the power to sustain the corona is actually a tiny fraction of it. So orders of magnitude smaller. So there's plenty of energy to sustain the corona, but that doesn't mean that it's not interesting. Okay, I mean, the world produces enough food to feed everyone, but you still have hungry people. So the question is not whether there's enough energy to heat the corona. The question is, what's the physical mechanism that heats the corona? How is it channeled? How is it supplied? How is it dissipated? But one thing that often is not mentioned when people talk about the coronal heating problem or conundrum is that they'll present it this way. Wow, so the solar interior is really hot, and then you go towards the surface, it gets cooler and cooler. So why does it suddenly get hotter again? Okay, but now if we look at the density in the solar interior at the core, it also goes down, and then it doesn't go back up. It's a tiny. So now if you look at the internal energy density or the pressure, let's look at the pressure. It's actually continues going down all the way to the corona. So first of all, the corona is really tenuous, not dense at all. And so yes, it's 1,000,000 Kelvin, but actually the energy content in the corona is very tiny. So the analogy of thermal conduction in a metal rod, that's you shouldn't have heat flowing from cool to hot to heat up one end of the rod. It's not a very good analogy because of the very high difference in the density. Okay. The presentation notes. Do you mean like the notes in Keynote? If so, there are no presentation. The slides, yeah, they should be made all available eventually. Is that right?
Yeah, we're also recording it, so the recordings will also be made available. So both of those things will be made available to everybody later.
Right. So there is. Okay. So yes, there's a lot of energy to hit the corona, but we don't really know what exactly is the mechanism which dissipates the energy, the way it's exactly carried. So those are open problems. The rest of this lecture will pretty much focus on the Solar Dynamics Observatory. And so that's a very biased view because I've been with the SDO team for a long time, and SDO provides the whole heliophysics community a lot of data that they use for this, the core of their science or as context. So I think it's very important that any heliophysicists become a little bit familiar with the SDO data. Okay. So it was launched in 2010. It has 3 instruments. It's pointed at the sun all the time and delivering data 24/7, almost all the time, science data. Of course, sometimes there are some like Earth eclipses or lunar eclipses which block things, and then there are calibration procedures. And very rarely there are anomalies on the spacecraft and instruments which require us to restart things. But it's basically been running continuously since May 2010. And it's been delivering about 2 terabytes of science data every day since then. So SDO in a nutshell, there are 3 instruments. There's the atmospheric imaging assembly, which gives you in certain wavelength bands in the visible UV and the extreme UV full disk images, which correspond to different layers of the atmosphere. And they're at a 4K by 4K resolution. There's the helioseismic and magnetic imager. I already showed some data from HMI before. It basically measures visible light, intensity grams, and by taking them at different wavelength positions and at different polarization states, you can measure the Doppler speeds of flows at the surface as well as magnetograms. And from there on, you can do a bunch of other things. There's the EUV variability experiment, which gives you disk integrated spectral irradiance data at 1 angstrom resolution, focused on the EUV. An example of a movie that you'll see from AIA, and you see a lot of these sort of movies, is flares and eruptions. So this is a multi-channel movie of a coronal mass ejection coming out of an active region, and you see these blobs of material leaving the sun's gravitational field. You get these like slinky-like loops behind. See, okay, yeah, I'm just looking at the chats. So you can study active regions from emergence to eruption, of course, except when they're on the backside. Not all the material from an eruption escape. Some of them fall back down. So this movie was taken in the 304 angstrom channel, which corresponds to singly ionized helium. So it's basically a transition region line. And you see that when some of the blobs fall back down, they brighten up. So some people have not just done heliophysics with this, they've modeled blobs falling down and hitting the surface of a star, and consider these to be templates of stellar accretion events. So this is what I mean by looking at the sun as an astronomical object. Okay, so let's walk through the different types of data that we get. From the HMI instruments, you get some, okay, it's not exactly continuum because it's not very far away from the line, but it's quasi-continuum. So like a white light image that we are used to seeing with sunspots. If you take these at different wavelength positions, different polarization states, you can combine them into these Doppler images. And the most prominent thing about this Doppler image is that you have redshift on the right side and blue shift on the left side. The redshift corresponds to flows going away from us, blue shifts towards us. So it just shows the rotation of the sun. So that's the most prominent Doppler signal you would see from the sun. But if you now subtract the average rotational flow, then you would enhance all these little fluctuations, waves at the surface, like ripples. And then you can use those ripples to look at power spectra, and from modeling what goes on in the interior of the sun and matching the power spectra, you can diagnose the internal structure of the sun. You can diagnose the rotational flows in the sun and also some other flows. And you can also image the backside of the sun by using helioseismology. So if there are big active regions on the backside of the sun, they would affect the acoustic signal to the point that you'll be able to detect them before they rotate onto the front side. This is a magnetogram. This is from AIA, a 171 image, which is basically transition region / corona. Let's go to this one, 304. We saw a 304 movie before. 193 angstrom. 1600 is a UV channel that's showing basically the base of the chromosphere. You can see that where there are magnetic fields, even outside a sunspot, there's a lot of brightenings in the UV. 335 is a different temperature range, and I'll discuss that in more detail later. In the center is a spectrum. It's evolving in time from the Eve instrument. So the Eve actually has a pinhole camera at this wavelength range, at the low I mean in the short wavelength range, and then in the EUV range where AIA has channels, it measures the spectral irradiance integrated over the disk in the EUV range. This next A channel unfortunately had an electrical anomaly in 2014, so it hasn't been delivering data since then. Okay, this is a blow I should have seen showing this one. So there's a pinhole camera in this wavelength range showing some low res images of the sun, and then there's the EVE Max A spectrum. Okay. So when you look at the EVE Max A spectrum in detail, you'll find a lot of spectral lines. And then if you look at the different wavelength ranges that are covered by the different AI channels, you see that they don't cover just a single spectral line. There's a lot of things going on. Okay. People use EVE a lot to study the sun as a star and to look at how the total output from the sun varies. So Tom Woods, the EVE PI, made a discovery early on in the mission about so-called late phase flares, and that is that in these late phase flares that last several hours, you can have the EUV output, which contributes to a large fraction of the total energy irradiated from the active region. And these are typically not covered in soft X-ray observations. So if you're using GOES soft X-ray observations to drive your upper ionospheric, thermospheric model, you might be missing the energy. In fact, many people don't even use soft X-ray data for that. Many people use some proxies like F10.7 radio data. But this was a discovery about the energetics of flares, which was not known before. So this is the so-called late phase in this region. There was a huge bump. Okay, now suppose we want to really interpret what the AIA images mean. Okay. Time check. I have 20 minutes left. Is that right?
Yeah, a little less.
Yeah.
17.
Okay. Yes. So often what you might find in some posters or some websites is that the 94 angstrom channel might show hot plasma at, I don't know, 9 megakelvin, 131 might be 11 megakelvin, something like that. 171 might be 500,000 Kelvin. This might be 1 million, 2 million, and it's all a lie. Because as I showed before, in each wavelength band, there are actually several lines. Now, so when you actually model what is the response of the AIA channels with respect to plasma temperature in the corona, it turns out that each channel has a broad temperature response. In the x-axis here, it shows the electron temperature, the log 10 of the electron temperature in Kelvin for each channel. And you see that for example, the 171 channel, it peaks at around 1 million or so, but there's also contributions from lower down. And then 193, there are 2 humps really. In the orange, again, 2 humps. So if we really want to do thermal diagnostics of the solar corona, we need to disentangle this multi-thermal response from the potentially multi-thermal nature of the solar corona. When you work out the math of how the signal forms on AIA, it turns out that if let's say you consider the signal in the different channels after you've aligned all the images is a vector with 6 values. Okay, so that's let's call that X. That's what you measure. Now you want to find Y, and Y is the so-called emission measure. The emission measure is the line of sight integral of the electron density squared. Well, why is it the density squared and not the density. The reason is that when you consider the radiative mechanism in the corona, typically it's dominated by collisions. So these are multiply ionized species of metals like iron, for example. They might be like 10 times, 11 times ionized, and in that state, they are collisionally excited to a higher energy level, and then the return emits that photon in the EUV. So they're collisionally excited, and that's why the brightness we see in the EUV is proportional to the density squared, because that density squared determines how often collisions occur. So you can write this relationship between the measured signal in different channels and the emission measure, which is a function of temperature, as a linear equation connecting the emission measure as a function of temperature and the observed signal. Okay, so this lists for the different channels the considered main contributors of emission. This paper, the way it works is you use an atomic database like Chianti. So Chianti is a very famous atomic package, and you consider you solve for an equilibrium state. It's called the coronal equilibrium, what I mentioned about how things are ionized. I mean, not ionized, excited. For an equilibrium state, how much would be radiated from different lines at a certain temperature, and that depends on the abundance of these elements in the solar corona. But suppose you assume a certain abundance that people typically report, then you can predict how much of the radiation is coming from a magnesium line versus an iron line or multiple iron lines versus the continuum, the Bremsstrahlung. So you have a model spectrum, and then if you, for a given temperature, and then if you then fold that model spectrum with the AIA spectral passband, then that tells you what would be the signal in that passband. So you do that for all the channels, you do that for different temperatures, and then that gives you the basically these response functions. So each of these curves is a row in the matrix here in this linear program, in this linear model. Okay, so yeah, so X is the observation, Y is what you're wanting to seek for. You want the emission measure as a function of temperature, and this matrix is calculated from the model of what you think the plasma does, and it also is it depends on the basis functions that you want to use to describe this emission measure. Okay, now it turns out that so this is an underdetermined linear problem. There are multiple solutions, but what do we? How can we pick the good one? Well, there are certain constraints. The constraint is that each value of Y has to be non-negative, because these are proportional to the line of sight. But they're basically the line of sight of the density squared, so they cannot be negative. And you can impose another constraint, and that is you minimize the L1 norm, or the sum of the absolute values of Y. Basically, this will choose the simplest solution, the simplest Y, or the Y that has the least amount of emission measure, that will explain the signal. So if we make that assumption, then we have a code to solve for DEMs. And why do we want simple solutions? Because it turns out when you do this, it doesn't tend to overfit. You're ensuring non-negative solutions. And you can use standard techniques from the compressed sensing community to solve this. It's very easy to solve. and it's relatively fast enough that you can make maps. Now, unfortunately, we still have the instrument team still needs to port this solver to Python. There are people who are, Joe Plowman, for example, I think is incorporating this into his package that is being prepared. There are different solvers with different assumptions on how to solve this DEM problem. But the one that is released with the AIA IDL package is using this method. Okay, so when you apply this to stacks of images at 6 different AIA wavelengths, then you can get a so-called emission measure distribution that looks like this. So here, this movie scans in temperature space, and this is of an active region. And what we see is that so at the lower temperatures, at the lower temperatures below 1 megakelvin, you see these fan loops at the edge of the active region. If you go to higher temperatures, you see at about a megakelvin or so, you see the core of the active region. The higher temperature you go, the more central you see the loops. These are because these are connected to the strong fields, and where there are where there's shear in the magnetic field that allows the plasma to be heated to 10 megakelvin or so. So you basically have a sequence of temperature maps showing where the hot plasma is, the warm plasma, and the cool plasma is when you solve that DEM problem. Now, as a validation of the DEM solver, the method, you can then use that DEM solution and multiply it by the temperature response function of an X-ray telescope, like the Hinode X-ray telescope. And so for one of the channels of XRT, this is the real observation. And the synthesized X-ray image is this one. So this is using the AIA DEMs, doesn't use XRT data. And this is a comparison over a few orders of magnitude. Actually, it does fall along a diagonal line, and the higher the signal, the tighter it is. But actually, there's an offset of a factor of 2. So there's some intercalibration discrepancy between XRT and AIA, and that's known also between XRT and other instruments. We don't really know why, but it falls on a very tight diagonal line. So same thing with another channel for XRT. So basically what this tells you is that, right, with AIA, you can do thermal diagnostics with of the corona, even though the AIA channels are multi-thermal. And also, if you look at an XRT or X-ray image, it doesn't necessarily mean that the plasma you see in an X-ray image are hotter than the plasma you see in an EUV image. Despite the general assumption is that X-rays are higher energy, hotter. That's not the case. So that's something to keep in mind. Okay. So let's think about flares. I have 5 minutes, 6 minutes. This is about observations and data. So I won't go too much into the model, but nevertheless, I want to quickly tell you about MHD, and you'll learn more about that tomorrow from Antonia. In a certain sense, MHD is quite simple to visualize. You have mass conservation, you have momentum conservation, you have energy conservation, and then you have Faraday's law. Okay, so Faraday's law. So you have dB by dt is minus the curl of E, which is not that easy to visualize, but in highly conducting plasmas, like in the sun, and consider that we don't have any diffusion or it's negligible, then the electric field can be written such that it just looks like minus the velocity cross B, where velocity is the plasma, bulk plasma velocity. Okay, this is a very simplified MHD. Now, when you get to this equation, it's still hard to visualize. But let's say you then write it into Lagrangian form. So if you follow a packet of plasma with some magnetic field, you want to know how does that magnetic field change? Well, it only changes because of two effects when you're following the plasma. It changes because the plasma is compressing. You have a divergence of V. When it compresses, it will increase the magnetic field strength. And it changes because when you calculate the gradients of the velocity field and project it onto the direction of the magnetic field, it's a line. So if you have a gradient of the magnetic field in the direction of the magnetic field, it's stretching the field. So those two things are enough for you to help visualize how the magnetic field changes in highly conducting plasma. Okay, so that's why in a lot of solar applications of MHD, people draw field lines and then they think of field lines having an identity in time. Whereas in a normal lab environment on Earth, when you think about magnetic lines of force, there's no identity that is kept from time to time. Okay, so people have models of how flares work. They generally consider that there is a current sheet, oppositely directed magnetic field. And when the magnetic field does reconnect in a very small region, the magnetic field now has a new configuration that has a high curvature and it relaxes. And the relaxation of the magnetic field, as the field line is like coming out of the reconnection region, it accelerates plasma and it heats up things, okay? So using the temperature inversions I showed before, let's look at a flare on the limb of the sun. The color coding tells you the sort of like an average temperature. And actually, I'm going to skip this slide and just go straight to this one. Okay, so the color coding tells you the color coding tells you the average temperature. And the contours tell you how much emission measure there is. And what you find is that when a flare occurs, the temperature is very homogeneous because the electrons in the corona are actually very mobile, and then they can conduct energy along the magnetic field line. But then the compression causes an enhancement in the density locally here first. And then because all the energy being conducted down to the lower atmosphere is dumped in the chromosphere, you get these evaporation flows. So it's consistent with some MHD models of flares. So you can use AIA to diagnose how flares evolve temporally. I want to quickly end. No, okay, I have to do this. I have time for this. In numerical models of flares, we can do MHD models of flares that create all these hot temperatures. Okay. Now let's say you synthesize the X-ray signal. This is the soft X-ray signal from GOES from this simulation. It's fine. It goes up quickly. It drops off gradually. If you look at the X-ray spectrum, like what a RESI instrument would observe, a RESI was a small explorer that is no longer working, but it worked very well for 16 years. People find that there are power laws in the X-ray spectrum. And usually this power law is interpreted to be signature of non-thermal plasma. What we found from the simulation is that even if you didn't consider non-thermal processes, from the MHD simulation, because there's a distribution of plasmas at different temperatures, just by adding all those temperatures together, when you consider the thermal Bremsstrahlung, you also get a power law. The point is that just because something looks like a power law doesn't necessarily mean that there is like a non-thermal behavior. It might be multi-thermal. It doesn't rule out that there's non-thermal, like departures from Maxwellians. Of course there are, but one has to be careful because very often in the literature, power laws are taken to be signatures of a non-thermal nature of plasmas. Of course, the emission processes can be non-thermal, especially if you look at the radio. So the expanded Owens Valley has been giving great data of solar flares. This is 13 baselines of radio telescopes. Usually the sun will look like this, but in a flare, it will look like this. And when you do forward modeling of the radio, the millimeter emission, including the magnetic field, you will find that you can diagnose the magnetic field in current sheets in flares. This is a really nice paper by Bin Chen et al. Really nice. They can fit for different regions here, using the spectrum of the radio spectrum, what the magnetic field might be in the current sheet. So in the future, we're going to have a high resolution spectrograph called EUVST. That's a Japanese-led mission. We're going to have DKIS and other ground-based telescopes. And we're going to have the multi-slit solar explorer, which will combine to give us what we call the next generation solar physics mission. So a lot of the fine scale structures and processes that I've been discussing could be studied with these three components. The EUVST and MUSE will likely be launched in 2027. I don't have conclusions. Really, I have a list of, I do have a conclusion. Go see a total solar eclipse. I have other references. And with that, I will finish and ask for questions.
Yeah, so there is thanks, Mark. That was really great. There is a question in the chat from Pratik.
Yeah, so, right, so when you consider the plasma is thermal, then you basically is saying that you have a Maxwellian distribution. That's right. And a Maxwellian, so basically what happens in a lot of times when one fits the, what happened, whoops. When one fits the, trying to go back to the, when one fits the power spectrum from X-ray power, the X-ray spectrum, one might include a thermal component, and that would drop off very quickly. But then the rest, you just model as a power law, and you consider that power law to be a distribution of particles that are non-thermal. But I'm saying that you can just have a power law also of thermal distributions and match that. So you're right. That's you know, when you're talking about thermal, it means Maxwellian distribution. I'm just saying that there might be multiple Maxwellians, and in addition to whatever non-Maxwellians there might be. Okay.
And Miguel added something in the chat about the X-rays.
Oh, okay. So there are spectral lines in the X-rays, and then the bulk of the X-ray from the coronal source would be due to Bremsstrahlung. And then there are some hard X-ray sources in the foot points of flare loops, which is also Bremsstrahlung, but it will be considering that you have a fixed target where the energetic particles are suddenly completely decelerated, and then that causes the X-ray emission in the hard X-ray sources here. So yeah, Bremsstrahlung and line. So here there's a spectral line here, for example.
And Pratik has his hand up. Maybe he can unmute and ask his question.
Yeah, so corresponding to that thermal thing, so are you saying that there could be multiple species and their corresponding thermal emission, that Maxwellian distribution of energy could actually result in a power law?
Yeah, so from the model, because this is a single fluid MHD model of the flare, and well, it is energy preserving in that when magnetic field strength energy decreases, that goes into the kinetic energy as well as the, well, that goes into kinetic energy, and then the kinetic energy goes into the thermal energy mainly via shocks. That flow of energy from magnetic to the internal is interpreted in that it results in an increase in the thermal energy because it's just a single fluid MH2. But even with this simplification, of course, you get very high temperatures. But even with this simplification, when you then use these distributions of temperature in space in the simulation cube and model what would be the resulting X-ray emission from thermal Bremsstrahlung, and you add it all together, then you get a power law. And that's simply because of the different temperatures in different places all adding up to be like this. That's just the limitation of the model that we're assuming thermal. But in a sense, that's the temperature is just a summary of the kinetic of the energy density. So the Boltzmann constant times T is just a summary of the per particle energy density, and it preserves energy that way. And if you interpret that it is a Maxwellian distribution, calculate the X-rays, you get thermal at each point. But when you add everything together over the flare, it looks non-thermal.
Yeah. Okay. Yeah. Thanks. So, can you recommend anything to read it further?
Okay. So this is described in this paper.
Oh, okay. Yeah. Thanks.
Is there other questions? But I guess we have office hour too, so we have lots of time.
Yeah, so Nick, is there, maybe I'll toss it back to you, what you want to do at this point according to the schedule, which we're close to on time.
Right. I think we're pretty good on time. So the one announcement I have is that one of our lecturers for tomorrow, Antonia, who will be talking about solar modeling, as Mark alluded to, has a little bit of work for you. I'm trying to get a little bit of clarification about how she wants to organize this, but I've put in the time zone work groups in that channel some reading sections. I went over the readings, and each of the individual sections is pretty short, except that she wanted all of chapter 3, which is basically no MHD, right? Which, you know, either could be like, oh yeah, I know MHD, or it could be like, yeah, I can't do that between now and tomorrow, right? So I recommended that you review 3.4. She also has 6 of the activities that she recommended people review. Here's my suggestion. In your time zone groups, get together and at least read through the activities so that you know what the questions are. I mean, that's the half of the time is figuring out what's the question asking me, and then see what you can make of that and discuss how you might solve that, and then pick a couple and write up some notes. They don't have to be carefully written down, just so you have in your mind as a group what those what the solutions are for those activities. So and like I said, just pick a couple. So that's what Antonia would like you to do for our session tomorrow. And then one other request is that for the lab on Friday, I'm hoping to use something that requires you to have a GitHub account. It's not, you won't have to log on to GitHub, but your GitHub username will have to be entered into a particular set. So if you have a GitHub username, great. If you don't, you should be able to go to github.com. GitHub is this software repository for those who don't know. You should be able to generate an account for yourself, and then in the document that I have, if you can put your name and then your username, your GitHub username, That would be great. Questions on any of that? Do any of the time zone groups need time to organize yourselves? Going once, going twice. Okay, you're all like communicating with each other. That's great. All right. Good. Then that's all I have, and then we can handle Mark's question. How many of you have seen a total solar eclipse? And so you can either raise your hand if you've seen a total solar eclipse, or put it in chat along with your location, etc. Sorry, Pratik. I take it that means no.
Yeah, that means no.
So I've seen 4.
You've seen 4. Okay.
Show off.
Well,
You
don't
want
I
me
have
get
to
into
admit,
a
I'm quite jealous. Once you see one, it's what Mark said, you see one and then you're sort of so wowed, you kind of want to start chasing them all over the place. Unfortunately, they're not always at places that are easy to get to.
But the one in 2024, for people who are in the US, there are many places that are relatively easy to get to.
And
That's right. This
there's
could be a
also
huge
lots
thing.
of science going on for that. So like, get connected with somebody who's doing some science around it, and they'll send it to you they'll send you there for free. I think a related so if you have questions for Mark or any questions from today, please put them into the chat. Somebody asked me about recordings. Maggie, what are we doing about posting recordings?
Yeah, so they'll be posted on the website. I can let you guys know when they will be up. It might not be like the next day or so, but they will definitely be posted on there within the next 2 weeks. So.
So Mark, I have a question. Tess is in Dallas Fort Worth in 2024. Okay, so you should submit an abstract to Tess and give a talk. That's good to know. Mark, I have a question for you. In the very last, your very last thing you said was you rattled off 2 or 3 missions that were coming up for doing solar observations.
Yes.
Could you remind us of what those are, and what kind of opportunities are there, do you think, for early career researchers to get involved in those? Emerging and early career researchers. I'm starting using that term.
Yes, so I didn't prepare accompanying slides to describe the different missions, but I'll just say it verbally. So the Solar C EUVST mission is a high resolution, sub-arc second resolution, in fact, spectrograph, that EUV spectrograph that will have coverage of spectral lines that are sensitive to temperatures from the photosphere through the chromosphere, transition region, and corona, including the flaring corona. So in one instrument, in one spectrum, you can get all the layers of the solar atmosphere, and it will be sub-arc second resolution, so very high resolution. So that's very exciting, and it's a Japanese led mission, but with a huge contribution from the US side. So I'm sure there will be many postdoc opportunities that are related to studying the spectra, the data coming from EUVST. The multi-slit solar explorer is a spectrograph also, but it's different than most spectrographs in that there are 37 slits spaced apart, so that in order to raster an active region, it doesn't take minutes or tens of minutes. It just takes 10 to 20 seconds. So by doing that, you can capture the spectra all across the active region at the time scales of the corona, because the corona evolves so quickly. So whereas the solar CEUVST has very good, excellent temperature coverage, it is a bit slow in scanning. So MUSE can allow you to look at the spatial temporal correlations with the spectra. So that is also planned to be launched 2027. So again, between EUVST and MUSE, there will be lots of opportunities for postdocs to study how coronal heating occurs, how the different layers of the atmosphere are coupled. DKIST is operational already. In order to get observing time, you write observing proposals and then they select them, and it sort of depends on the conditions. What the sun, whether there's a sunspot on the sun or not. And the data is, I think, very different than NASA missions. The data has a proprietary period. So the PI who proposes an observing proposal might get 6 months proprietary period, and then the data becomes public. So there's a 6-month clock for someone to get the data from data to science. Whereas for all the NASA solar missions, there isn't anything like that. For example, for SDO, the data, you get near real-time data, which is not science quality, but almost very often is exactly the same as the science quality data. You get that within minutes. And within days, you get the science quality data with the right calibration. So there's no proprietary withholding period. Then that will be the same for EUVST and MUSE. So DKIST is a little bit different. But if you don't need the latest data, there will be too much data. So from all these missions, there will be too much data to analyze. We would need people who are very skilled at combining data from different instruments, at extracting physics out of spectra. And for the case of DKIST, especially spectral polarimetry. So it's a great time to do high resolution solar physics. And in order to do that, if you equip yourself with analyzing spectra, knowing about the atomic physics behind what goes on in the line formation, then there'll be great opportunities going forward.
Great, thanks so much, Mark. So, and there's a couple of questions so Christina has a response to this. You want to explain that, Christina, and then we'll go on to Lydia's question.
Yeah, so I think DKIST they do have this proprietary period, but I think it's double the length and I can't remember whether it's just grad students or grad students and postdocs, but in an effort to give them a little bit more time to analyze that without competing with everybody. It's longer. I think it's a year or double whatever the other one is. So that's kind of a nice thing to know.
Yeah, thanks
So
for
as a graduate student, you can make a proposal to DKIST and
absolutely
considered. Interesting. Okay.
Yep.
So the question was, if you had a flux versus energy graph, I guess that means like the X-ray spectrum in one of your slides, but with multiple peaks instead of one peak. Flux versus energy. Lydia, do you mean one of the very early slides of a spectrum, or the one with the X-ray? Just the X-ray.
the X-ray one. I think it's the second from last slide, or
So you mean like this one? Is
yep,
that what you
that's
mean?
right. Yep, that's right.
With multiple peaks instead of just one peak. Oh yeah, so these peaks are due to just spectral lines, and they would form for, I don't remember which line this is. They would form for a certain temperature, preferentially, but actually there'll still be a wide range of temperatures. So that tells you that there is some stuff there at that temperature, but the rest is all considered continuum, and so there is the background itself doesn't really have a peak. But if the spectrum had like just a peak like like this, then probably you can fit it with a single thermal distribution and do pretty well. I don't know whether I answered your question. So if there are two peaks, then you see like two populations. But the thing is that from AIA images and from other high resolution instruments, we know that the corona is highly structured. There's a lot of fine scale structure that is below the resolution elements of an instrument like RESI. RESI works with Fourier. RESI works like a radial interferometer, in that it basically samples in Fourier space and then you reconstruct. So there's a certain beam size to that, and the dynamic range is also, I think maybe 10, 20 or so, or 30. So it's not a very high dynamic range. And then there's line of sight effects. So it's highly possible, no matter how you think of it, that you're looking at different populations within the resolution elements or the field of view of RESI.
Okay.
Yep. Right. So we're still in office hours. I'm going to hang around. I'm going to show actually there are some links here about how to get the data. So for some of the slides I showed already, there are links on how to get the data. But here there are further links about how to get magnetograms and plot them, how to download AIA and HMI data from Stanford, and then some other resources. So there's a question by Perpita about, doesn't the SDO satellite get affected by solar flares? So actually the images, when you look at a raw SDO image, like this, like an image that's supposed to be like this, instead of like this, there are actually spikes everywhere, and sometimes some streaks of a few pixels. And those are due to most likely energetic electrons, but due to electrons that are accelerated probably around the region where there's the geosynchronous orbits, and not necessarily particles coming from the sun. Sometimes there might be huge flares that give solar energetic particles, which would impact this. But Christina would be the one to answer this question.
Yeah, so definitely it's the same sort of thing that you get with LASCO, is you can have the energetic particles impact the detector and cause these streaks and stuff like that. But also, Mark, sometimes if you get a flare that's really intense, right, it can bleed over from pixel to pixel, right? So you can get these effects where it kind of shows up even bigger than then it actually, yeah, that kind of thing where you get these vertical streaks and things like that, right?
Yes, yes. So for example, yeah, in one of these frames here,
yeah, there
you can see that on the CCD, because of the CCD has a well depth of 14 bits. If you get too many electrons, it bleeds over, and so you get this bleeding along these columns. So that's one effect when it's too bright. The other effect is that you get something like diffraction spikes. So you can see some diffraction spikes. These are due to the metallic mesh at the front entrance of the telescope. So when you have a very compact bright source, brighter than the rest, you get these diffraction spikes.
I think you had a good example of that on one of your last slides that you had shown, that you were on before.
This one?
Yeah, that one, you can see it in the left image. You can see this sort of cross effect. Yeah.
This cross. But actually, these, if there is no saturation, these diffraction spikes are pretty easy to remove. In the AIA, IDL, and Python packages, we have the deconvolution routine. Using the model PSF, it does actually pretty well when there's no saturation.
Right.
Yeah,